right, so for this first one, we have that the decathlon is a competition where athletes compete in 10 events. Two of those events are long jump and high jump. In both events, a greater distance means a better ranking. The table shows the results for these two events at the World Championships. So, for example, Germany for the long jump in its ranking is number one. Okay, and number one in this sense, because as it says here that a greater distance means a better ranking, that means that here they're first place. And as we can see, the biggest number for long jump is 7.64 meters. Do you see any number bigger than 7.64 meters in this column? I don't. It's the biggest one. So that means Germany is first. What is the second highest? Well, it's France with 7.52. So here they would be second. And as you can see, long jump ranking is an order. Okay, it's an order. It's nice and pretty. It's friendly. Okay. You're going to see in a second that for the high jump rank, it's not an order and there's some things we have to do. But let's go piece by piece. Let's see what happens. They tell us that Spearman's rank correlation coefficient, what the hell is that, is used to determine if there is a linear correlation, what the hell is that, between an athlete's ranking in long jump and their ranking in high jump. Alright guys, so before we jump into parts A, B, and C, which are honest, it's not that hard, but you do need to understand what is going on. Okay, so there's a lot of buzzwords here that some of you may not be so familiar with, so let's go piece by piece. A lot of this talks about correlation, okay? When we talk about correlation, the intuitive way to understand it is like, if X increases, how does Y increase? Okay? So, in this case, what they're telling us is if their score in long jump is, I don't know, around here, a very strong correlation means that the score in high jump is like the same level. See? So if it has a good score in long jump, then they have a good score in high jump. That would be a strong correlation. A correlation that's a little weaker might say, okay, they have a very good score in long jump, but not so good in high jump. See? And so this would also be a linear correlation. As you can see, I am also drawing a line, but the slope is a little bit less. If the slope of this one is, I don't know, 1/2, then the slope of the one I just drew was around 1, okay? All right, guys, just forget about slope for a moment. I know that can confuse a little bit, but the idea is if there is a strong correlation between long jump and high jump, it means that the better you are at long jump, also the better you're going to be at high jump, okay? Maybe another correlation that makes sense is like, I don't know, if you're good at chess, then you're also going to be good at whatever, like other board games, see? And that might make sense because chess takes a lot of strategy and thinking and stuff like that. So if you're good at chess, you're gonna be good at most other board games. If you're good at Counter Strike, then you're good at Call of Duty. If you're good at League of Legends, then you're good at Dota, whatever. Like I don't know, dude. Okay, you guys get the idea. So that is the intuition for correlation. Okay, so if there's a strong correlation, then like one thing sort of implies the other. Keep in mind that this is different than causality, okay? When we talk about causality, you need strong evidence to support it. You can have something with a very strong correlation, but a strong correlation does not mean that you have strong causality, okay? All right, whatever. So that's correlation in a nutshell. And when they talk about Spearman's rank correlation coefficient, the correlation coefficient is a number that tells you how strong that correlation is. So remember how I said just now that we had slopes, right? The correlation coefficient is a little bit like that slope. And so the strongest slope you can get is a slope of 1, okay? And so if your slope of 1 or your R that we're about to see is equal to 1, then that's a very strong correlation coefficient. If it's less than 1, you still have correlation, but it's a little weaker, okay? So that's what we're trying to do, okay? That's the correlation coefficient. And what Spearman does is just this guy that said, yo, for finding the correlation, we're going to be ranking our stuff. See, so that's why we have a column for rank. for long jump and a column for rank for high jump. So we're going to go ahead and rank long jump, rank high jump, put them next to each other and see if there's a correlation, okay? Between which two things? Long jump and high jump, okay? So that's a little bit of the context. I think it's very important just to understand what we're doing. And you're going to see that the method or the process for solving this is actually very, very fast, okay? So for part A, we need to complete the table to show the athletes' rankings in high jump. So as we can see, high jump is empty. Now, because it's a ranking, it works the same as the one right next to it. Let's remember, Germany is first because it has the highest value for long jump. France is second because it has the second highest value for long jump. Now, let's focus only on high jump. So for example, Germany for a high jump has 2.11 meters. Is there any country that is higher than 2.11 meters? I don't see any. So Germany, we're going to go ahead and say is first. Okay, so we're going to put number 1 here. Which one is the second highest? Conveniently, it's actually France right below. See? But now is when things start to get really, really weird. Estonia. Estonia, is it third? It's not third. See? Actually, which one is third? So we did 211, 208. What's next? I see a 205. It's probably this one. Do we see anything higher than 205? No. So we're going to say that the third rank is right here. All right, what about the fourth rank? So below 205, we have 202, 202, and I don't see anything else. All right, guys, and here is something interesting that occurs, okay? Because Canada and Ukraine are tied for fourth place, technically they both share fourth place, see? But because we're talking about Spearman's rank correlation coefficient, the key thing is that the ranking needs to be aligned. Like the first with first, the second with second, the third with whatever third is for high rank, the fourth with whatever fourth is for high rank. See what I mean? And so here you actually can't have them tie for fourth because in that sense it wouldn't make so it wouldn't like fit in. See? So intuitively, whenever they tie, in this case they're tying for fourth, you can think about it like this one's fourth and this one's fifth. But they're so close to each other that they might as well both be what's in between. So if we have fourth and fifth here, what's in between? Well, you have 4 plus 5 divided by 2. That's what's in between. 9 divided by 2, 4.5. That's what's in between. See? So because they're tying, you're actually going to put 4.5 and 4.5. See? Why 4 and not 5? Because it's in between. See, it's the calculation that I did. So whenever they tie, you're just going to take like a simple average, and that's that. See? And from here on out, it's a lot more forward. So there we have this one, this one, this one. What's below 2.02? Below 2.02, we have 1.99. So this would be, actually, do I have anything else? Hold up. 1.99. Yeah, so this would be sixth. And I know some of you right now are thinking, yo, what the hell are you doing? Point is, this one is technically like 4 or 5. And this one is also technically 4 or 5. Okay? And so we were forced to skip to the sixth. Okay? That's like the idea. I know that part's a little weird, but it all has to do with the fact that Canada and Ukraine tie. See? So you can think about the fourth and the fifth one already getting checked off. Okay? All right, cool. So that's why Grenada, I don't know if I'm saying that right. Sorry. It's sixth. What's seventh? What's below 1.99? This guy here, Japan. Number 8 would have to be this guy here, Algeria. Cool, cool, cool. Then we have Austria and finally Estonia, ¿cierto? All right. So that is literally part A. See, it's not that hard. The biggest thing you have to keep in mind is when they tie, what do? You find a simple average between both. Okay, that's the only way they can like sort of catch you. And be careful that Granada ended up being number 6. Okay, we didn't put number 5 for Granada. We put number 6 because technically the 4th and the 5th were already sort of like checked off. Okay, all right, whatever. For part B, we need to find the value of the Spearman's rank correlation coefficient, RS. So of course we need the calculator here, see? And so something that I talk a lot about in my videos is that a big part of this test, okay, or the IB in general for the math, is really just being familiar with your calculator, okay, being familiar with the formula booklet and stuff like that. Guys, the day of the test, you're gonna walk in, you're gonna have this guy right here, your calculator, you're gonna have your big brain, you're gonna have your formula booklet, you're gonna have probably like 2 hours of sleep and a lot of motivation to do well in this test, okay, and your brain. I don't know if I already mentioned that, but whatever. Pen and pencil, all that stuff. See? So, of all the stuff you're gonna be walking in with, you gotta feel good about it. Okay, you gotta know what's in it. Okay, and I'm not saying you have to know it by heart, but you do have to know where stuff is, sort of. Okay. For example, these are tools that you have. Okay, so imagine you're at home and you have a broken window. Okay, and you need a hammer to nail it, ¿cierto? And you don't know where the hammer is in your house, but you know what room it's in. Okay? This is no different. We need to use Spearman's rank correlation coefficient. And I'm not saying, ooh, where is it exactly? But I am telling you, okay, do you know which room to find it in? Okay? Do you know if it's distribution here in blue, or if it's the stat button, or if it's math button, like which one? Okay, that's that is the sort of stuff that you need to know. Okay? So I'm just gonna say it right away, but for this case, because we are calculating something, okay, you're gonna go stat, here you have calc and test. Okay? In this case, Spearman's rank correlation coefficient is technically like a linear regression. Okay, so here you have a lot of linear regressions, but none of these give you the Spearman's rank correlation coefficient. Okay, here you do have a line reg, but it doesn't give you Spearman's rank correlation. For Spearman's, you actually go to test, and it's all the way down in this thing called line reg test. Okay, so if you want your R value, you gotta do line reg test. So as you can see, I have two line reg tests. See, I have line reg int and line reg t-test. Okay, the int, as we can see, asks for a C level and stuff like that. It's a little weird. You're probably never gonna use it. Forget about it. Okay, so now you know for line reg test, you just use the other one. See, so if you see the thing that says C level, you're in the wrong one. Probably. Okay, I've never have had to use it for any of these tests. So I go over here, it asks for a bunch of stuff. Okay, and I know some of you might be thinking, yo, what the hell? What's going on? Take it easy. I got you. See? So on the one hand, it asks for X list. See? Basically, it's going to be your first list. So in this context, we're going to say that this is L1. Okay, and this is L2. So that means my X list is going to be my long jump, and my high jump is going to be L2. That's it. When it says frequency here, okay, intuitively that has to do with how much, like if this is a cumulative if this is a frequency table. Okay, so for example, if I put frequency 2, I might be saying like, oh, and this one appears twice. See, stuff like that. Okay, for this context it really doesn't matter, and for Spearman's high rank correlation coefficient, you're pretty much always going to leave it on 1. Over here, as you can see, it's a p-value. Okay, it's for calculating probabilities, how likely it is. Like that's for helping with causality, as I mentioned earlier. See, right now we're only focused on correlation, so you can actually put any of these three, and it doesn't matter because it's not going to change the value that we're looking for, which is just the correlation. See, so I'm just going to put the one in the middle. Doesn't matter. Okay, it really doesn't matter. Yeah, because I need to put the X list and the Y list, where do I put it? So I go to stat, edit. Okay, stat, edit. Here's my list 1, here's my list 2. Make sure you clear it out. A quick way to clear it out is go up, press clear, press enter. Go to the other one, press clear, press enter. Bada bim, bada boom. So list 1, I know it's not the most exciting thing in the world, but we are doing math, so I don't know how excited you might be, at least for some of you. You're just going to put the first list, which is from 1 to 10. Cool. The second one is a little more tricky. So I put 1, I put 2, here I put 10, here I put 4.5, 3, 4.5, 8, 9, 6, and 7. And here's an important point that I didn't mention earlier. So remember how this is Spearman's rank correlation coefficient? The cool thing about it is that one of your lists is completely ranked, like from 1 to 10, and the other one is a little more all over the place. See? And so you're going to have a strong R value if your L1 is similar to your L2. If they're very different, then your R value is not going to be as big. So for example, the first and the second, as we can see here, are the same. Okay, that's going to be a good R value. The second ones are also the same. That's going to be a good R value. But for the third one, there's already a very big disparity from third to 10th. Okay, that's a massive difference. My R value is going to be affected. For 4 and 4.5, similar enough, not the same. For 5 and 3, similar enough, not the same. And you can sort of say the same about the rest, okay? Except for 9 and 6 and 10 and 7, that's a pretty big disparity, okay? So I'm going to end up with a solid R value. I wouldn't say it's going to be an amazing R value. So, anyways, I go to stat, I go to test, I go to line reg, bada bim, bada boom, here it is, kapound, see? I never use the interval one, or the int, I use the test one, x1, sorry, x list L1, y list L2, frequency 1, you're pretty much never going to change that. This is probably anything you don't care about. Reg EQ is if you ever want to graph your thing and you want to put it in your y equals, you need to put like y1, y2 in here, okay? We're never going to use it, so we don't care. Go ahead and press calculate. A bunch of stuff shows up. So as you can see, the first like 4 or 5 things have to do with the probability thing I was talking about, like the causality, the test we were running, okay? Because you can run a test like, okay, how similar are these? Like to what probability, to what significance level, all that stuff. Okay, that's here, yeah? And depending on whether you ask, not equal to 0, less than 0, greater than 0, you get different results, okay? But we don't give a shit. We don't give a flying fuck because all we're going for is scrolling all the way down and getting that R value. See? So R value for part B is going to be R equals 0.541 with 3 significant figures. See? How do I know it's 3 significant figures? Because for 3 significant figures, you go 1, 2, 3. You see if we're rounded up or down, it stays the same. So 3 significant figures is like that. Okay? All right, cool. And it really, really doesn't matter what you put, okay? You can put, oh, what if p is not equal to 0? You're going to see that the values up here, like the first 4 values are going to change. See, remember that my p value before was like 9, 6 or something? Well, now it's 0.1, okay? But my r value, which is what we really care about, doesn't change. And that's what really matters for us. So whatever, okay? That's part B. Finally, part C, very straightforward. We have that the following guide is used by the coach to determine the strength of correlation. Strength of correlation. So remember, you have this correlation, right? We have long jump and high jump, okay? A very strong correlation is if it's a linear relationship, see? Like with a slope equal to 1, right? So this would be a strong correlation, right? They have the same slope. That's very strong. It might be a little weaker if the slope goes something like this, okay? Because as long jump improves, high jump also improves, but not as much. Okay, that's the whole idea, not as much. So let's see what's going on here. Basically, if your R value is between 0 and 0.199, it is very weak. If your R value is between 0.2 and 0.399, it's considered weak. So in this case, because my R value is of 0.541, what does it qualify as, you guys? It qualifies as moderate. Okay, 0.541 goes into the moderate category. And still, for part C, we need to state the strength of the correlation between the rankings as indicated by the table and interpret this in the context of the question. So, there's a lot of different ways to answer this, but immediately you have to say the correlation is moderate. And I guess you can give a short explanation because 0.541 is between 0.400, and 0.599. So just with that, you already have 1 point, okay? For the second point, there's a lot of different ways to put it, but I'm just going to put what the answer key says. Okay, the answer key says, as long jump ranking increases, high jump ranking will likely increase, okay? So that's going to be for your second point, and you're good to go. If you don't like how the answer key puts it, you can put something that's very, very similar, okay? And so what I would do, just because for me it's more intuitive, I would say as long jump ranking increases, high jump ranking increases moderately. See? I don't know how the hell to say that. Moderately. Moderately. I think it's that. Moderately. Alright, whatever. Who gives a shit? See? That is part C. Alright? So guys, as you can see, if you take this video and eliminate all the intuitive concept explanation part, you do this right away, dude. Okay? It's a quick problem. It's quick points. But if you show up and you read Spearman's rank correlation coefficient and you have no idea what the fuck it's talking about, dude, you're gonna miss on 6 easy points. Okay? Guys, for a lot of this, just knowing a little bit gets you a long way. Okay? For example, I think it's in this test, but later on it talks about something that's the normal to the curve. There's a lot of sort of buzzwords and vocab words that if you don't know, you're just like, you're fucked, okay? The normal to the curve is like, it's the perpendicular to the tangent, okay? I'm not gonna get into it. I have videos on it. But the idea I'm trying to tell you guys is that there's a lot of vocab words that if you don't know, you can't even get started on the exercise. Okay? You need to know the intuition of each exercise. All right? And I'm not saying you have to know it by heart. I'm not saying you have to know like everything like perfectly mathematically, blah, blah, blah. No. But I am saying you gotta understand the intuition. Okay? If it talks about correlation, it's gotta ring a bell. Okay, if it's talking about Spearman's rank, you gotta think, that's a tool I have in my toolkit. I know which room it's in, but I just gotta find it. So you're gonna be in the day of the test, you're gonna be looking at tests, trying to find it, and eventually you find something that says line reg. Right. It's a line reg because we're going for a correlation. Kapow! See what I mean? So it's that kind of stuff that really helps. Okay, just knowing the intuition, knowing the methodology for the exercise is key. Ladies and gentlemen, that is the first one. I hope it helped. Alright, so for number 2, we have that point H. That means this guy here on a hot air balloon is sighted at the same time by 2 observers. Ooh, exciting. One observer is at the top of a vertical building that is 156 meters tall. Cool. So that is this guy here, point A. The other observer is at the base of the building, point B. Alright, cool. The angle of elevation, what the hell is elevation? I'll talk about it in a moment. From point A at the top of the building to H is 40 degrees. Alright, cool. The angle of elevation from point B to H is 57. Point X, this guy here, is directly below point H. That means I have 90 degrees here because it is, just directly above H. The information is already shown in the diagram. Thank you, IB, for being so kind to us. So, before we jump into part A, let's talk a little bit about what the heck is angle of elevation. So, in these trigonometry problems, I need you to know these 2 sort of buzzwords, buzz concepts, whatever. The first, of course, is angle of elevation that can show up in trigonometry, and angle of depression can show up in your teenage years as well. Anyways, I need you to have the intuition that angle of elevation is from the bottom to the top. And the angle of depression is from the top to the bottom. Now, for some of you, that is certainly not enough, see? And even for me right now, it's kind of like, what? What is that, see? So, let's say that I have 2 points, okay? Let's say that I have point X and point Y, okay? If I draw a line between these two, okay, there are certain angles that show up, okay? let's talk about angle of elevation first. I'm going to do it in red. Okay, so elevation is going to be in red. So if angle of elevation is from the bottom to the top, you can think about it as an elevator. So you take an elevator to reach a higher floor, okay? And so basically, you would say, what is the angle of elevation from x to y? That means you draw a flat line on x, okay? That technically goes like this as well, but you draw a flat line, all right? And you think, okay, how many degrees do I go up until I reach y? So for example, you can have this angle here, which could be, I don't know, maybe 10, see? You have this angle here, which is, I don't know, like 5 more, etc. And you keep drawing these lines until you reach, until you reach y, okay? And so once you reach y, you are drawing this triangle here, which means it is this angle there. Kapow! That is the angle of elevation, okay? That is what they mean from the bottom to the top. You keep drawing lines until you reach y, and whatever line reaches y, you do your triangle, there is your angle, okay? Cool. Kapow! So this would be my elevation, okay? Angle of elevation. What happens with the angle of depression? So depression, we're going to do it in green. So the angle of depression is similar, just that it's like the other side of the coin. See, so again, since it's from the top to the bottom, okay? When you're depressed, you look at the floor a lot, dude. I don't know, whatever, okay? You draw this line up top horizontally, okay? And you ask yourself, from point Y, how many degrees do I need to do until I reach X? So I keep going, I keep going, I keep going until finally, kapow, I reach X. It goes like this. And this angle here would be, you said it, my angle of depression. Depression. Okay? So that is what they mean by angle of elevation and angle of depression. That is also how you get it. So in the context of this problem, when they tell you that, yo, from point A to point H, the angle of elevation is 40, you can see that they kept drawing lines, right, until reaching H. And once they reached H, they said, okay, what is that angle making a flat line on A? It was 40 degrees, okay? That is how they got the angle of elevation. And it's relevant to know that because for part C, they talk about angle of depression. So you might know what depression is, probably. You're probably a teenager watching this, so yeah, you know what depression is. But angle of depression, that might be new to you, okay? Anyways, whatever. Good to know, shows up in trigonometry, there you go. Now we can start talking about the problem. So for part A, they ask us to find the size of angle AHB. So when they put it in that order, they're asking for angle H, see? Now the angle of angle, the angle of angle. Angle H, which is next to A and B, see? So you're going to look at AHB and say kapow, kapow, kapow. There's my A, there's my H, there's my B. What is the angle that is formed by those lines? This guy here, see? So that is the angle that we are trying to find, okay? So basically, your compass, okay, like your north, what you should always be looking to do in these trigonometry problems, look at it. Trigonometry problems, see? Triangles. Focus on triangles. Think about triangles, how you can fill them in, what information you're missing, etc. And so if I look at this triangle here, the one that I'm going to put now in, whatever, in yellow, see? This guy here, see? Try to find everything you can in regards to this triangle, see? And if there's information you're missing, okay, maybe you can get it from the triangle that's right next to it, okay? But you always gotta be thinking in terms of triangles, okay? What can you fill in, what can you not, etc. So, this triangle that I'm talking about, the one in green, the AHB, is next to a building, see? This building is a rectangle. And so if it's a rectangle, you have 90 degrees all around it. Kapow, 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 kapow. That means that right next to it, you have 90 degrees as well. Ah, interesting. So if I have a 90 degree right here, that means I have a 90 degree right there. Okay, that means this whole thing is also 90 degrees. All right, where are you going with that? Well, first of all, the case up here means that this whole angle, ¿cierto? Is going to be 40 plus 90. So that whole angle is actually 130. So that whole thing, ¿cierto? This whole thing is going to be 130, okay? The whole thing. That whole thing is 130. And I'm actually going to cross out this 40 so that we don't get confused. Okay, that whole thing is 130. All right, what about down here? Well, down here, if this whole thing is 90 and this is 57, then this is the remainder. So I can say 90 minus 57 is going to equal quick maths, not so quick maths, 33. Yeah, so that means that over here, see, this guy in red is going to be 33. All right, and so now suddenly this exercise is much more feasible, it's much more approachable, etc. The sum of angles of a triangle is 180. So 180 is going to equal this 130 that I got in green plus this 33 that I got in red plus my favorite angle AHB, which is this guy here. See? So that means that 180 equals 163 plus AHB. That means that if I subtract 163 to both sides, I end up with AHB being equal to 17. So that is for part A. For part A, we found that the angle is 17 degrees. All right, for part B, we need to calculate the distance from point B to point H. So again, now I'm sort of like pulling out this triangle, see? So I'm pulling out this triangle that goes like this. This is for part B. I have the point B, the point A, the point H. I know that this angle we said was 130, if I'm not mistaken. Yes, this one right here is 33. And what I just got from part A, this is 17. See? What are they asking for? They're asking for the distance from point B to point H. So that is this guy going over to this guy, see? Which in the diagram, which is the same triangle, is this guy here. So this X, see? This whole guy, this X. All right, cool. How the hell can I find that? So, in trigonometry, you have a couple of tools you can use, and actually, give you a moment, I can pull them out. Give me a second. Doop-de-doo. Analyzing, analyzing, analyzing. Kapow! Here's my formula booklet. See? The day of the AP exam, you were walking in with a couple of things. You're walking in with this guy. You're walking in with your brain. You're walking in with a pen and pencil, your graphing calculator, and everything you've learned, and the full confidence you have in yourself. So, trigonometry. See? Well, let's see. I have Geometry and Trigonometry, topic 3, page 6 and 7. It's important to get familiar with it, to know the tools that you have, the tools that you don't have. And this is the big stuff for trigonometry. Okay, you have sine rule and cosine rule. Now, I have some videos that detail this a lot, but basically, I need you to think of sine rule as pairs. Okay? And for cosine rule, you're gonna use it if you don't have pairs. I'm not even kidding. That is probably the best way to do it. Okay? If you want to detail cosine rule a little more, it's kind of like missing one. Okay? If you're missing one angle or you're missing one side, you use cosine rule. All right? But yeah, whatever. See? Now, let's think about pairs first. See, can I make Can I make pairs in this triangle? What I mean by pairs. If you see the formula over here, can I actually screenshot this maybe? I cannot paste it here, that is unfortunate. Anyways, for the sine rule, okay, so sine rule, I'm gonna do it here. So sine rule is little a divided by sine big A equals little b. This is divided by sine big B, and little c divided by sine big C. Now, as you see, you have two equal signs here, see? So technically, you can use whichever pair you want, okay? So, whatever, I'm just gonna use the two on the left, okay? Now, what is little a, what is big A, what is little b, what is big B? Intuitively, it's the following. Let's say you have a triangle, okay? If this is angle A, notice that it's a big A. If this is angle A, that means this is side little a. If this is angle B, that means this is side little b. If this is angle C, that means this is side little c. Okay? So, what's the intuition? Big letter, angle. Small letter, side. So, when we talk about pairs, we're talking about pairs of angles with sides. Ah, okay, so this x, this side x, is paired with this 130. Okay, and so right now, if I apply the sine rule, I have x divided by 130 equals something else, cierto? For example, AH, see this AH here, and that would be the side 33. I mean the angle 33, see? So sine 130, sine 33 over here. So as you see, I have two variables. See, I have the variable x, the variable AH. And so what you need to do is find another pair. See, find more information so that you end up with a pair. See? Now I needed to do that whole blah blah so you guys understand why we're doing what we're doing, okay? If I were to just show you the answer, like, what the hell is that going to help you for the test, right? So we're going for pairs because sine rule works in pairs. And when I talk about pairs, I'm talking about an angle with a side. How do you know which is which? Big letter, angle, small letter, side. Draw this diagram, don't forget it. So let's go back here. Is there anything else I can get from here that can give me maybe a side of one of my triangles? Well, something that's cool about the IB is that usually, or at least what I've seen, is that all the information they give you is usually information that you end up using. And so let's look at the information that they have given us that we haven't used yet. For example, we haven't used yet this, this 57, we used it to get the 33, see? I don't think we've used yet the 90 degrees, and we haven't used yet that this building is 156 meters tall. All right, there's my hint. So, if you haven't seen it yet, I'm going to tell you. This 156 height of the building is the same 156 over here, which is actually the distance of A to B. So the distance of A to B is the same height as the building, which is 156. What units? Meters. So if I go down here, I actually have 156 as a side. Side AB is 156. Ah, so there's my other pair, see? So my first pair, I already put it. The second pair is going to be side 156 with sine 17. That means that if I want to get x alone, I cross multiply to both sides. I end up with x times sine 17 equals 156 times sine 130. That means that x equals 156 times sine 130 divided by sine 17. I trust the process. I put all of that into my trusty rusty calculator. If you want to do it quick in a fraction, you can press alpha, y equals. Alpha y equals brings out this little tab. You press the first one. Boom, you have a fraction. It just looks kind of cool. You don't have to do it, but I think it looks cool. So, 156 times sine 130, close parentheses, don't fuck it up, divided by sine 17. Cool. How much is this? That. So we have, with significant figures, 408.0 736. Let me actually put everything first. 736, 314. See? Actually, just whatever. 736. Let's just leave it there. See? If you want to do three significant figures, you count 1, 2, 3, and this third one, you see if you round it up or down by comparing it to the one next to it. So if I have a 7 next to it, it's above 5, you round it up, you can leave it as 409. Don't forget your units, meters. So this x that I put before is actually, and I'm going to put it in a fancy color, is actually 409. Okay? Cool. That is for part B. Then they tell us that the hot air balloon remains at a constant height as it moves further away from the building. Describe in words the change in angle of depression, ooh, fancy words, from point H to point B. From this guy to this guy, ooh la la, as the horizontal distance between the balloon and the building increases. So, first things first, when they tell us it's a constant height, that means it is going to be the same height, okay? Same with an M. Apologies for my wonderful handwriting with a mouse. Same height is constant height, okay? That's also why in math, when they talk about a constant, so let's say you have, I don't know, like f of x equals 3x squared plus 2x plus 7, and they talk about constants. Your constants are 3, 2, and 7. What can change in this equation is the x. X can be pretty much anything here, okay? But your constants are in red. No matter if you plug in x equals 100, x equals 69, or x equals 420, you will always end up with the same constants, see? Your answer is going to change, yeah, because in one scenario, you're plugging in 100 squared, and in the other scenario, you're plugging in 69 squared, okay? Of course, this is going to be different, your final answer, but hey, your constant is the same. Ooh la la, okay, that's constant, it never changes. Ah, okay, so the height of this guy is not gonna change. That means we're gonna move over, I don't know, over here, and my balloon is gonna be here, and the height is the same. The height is the same. So, describe in words, okay, we don't have to show anything. Describe in words how the angle of depression changes, see? And this actually goes back to what I showed in the beginning, see? So, let's say I go further down the line. I go way over here, okay? How do you think my angle of depression is going to change in respect to x? If I go ahead and draw it, the angle of depression goes like this, ¿cierto? I count until I reach x. I end up with this, see? Which angle do you think is bigger? The green one or the orange one? Now, of course, visually, it's not like, I guess, so easy to notice it. So maybe use actually a little bit of imagination, see? Imagine here is someone you know, your friend, whatever, okay. And you are in a hot air balloon because why the fuck not? Okay, you're in a hot air balloon, see? Your friend is not moving, but the hot air balloon is, okay, at a constant height. Think about it. Think about the angle of your head. If you were very, very close to your friend in this hot air balloon, if you were very, very close to your friend in this hot air balloon, how would the angle of your head be? Dude, you would be looking like almost out of the balloon straight down, pretty much, okay? So the angle of depression when you're very close is very big. But if you're very, 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 very far away, the angle of depression is much less. Ah, okay. So that makes a little more sense. Again, if you're very, very close to your friend, you have to look almost straight down. The angle of depression is very big. If you're farther away, your head isn't so tilted. See, you're looking more into the horizon, you're looking more horizontal. The angle of depression is smaller. So, what is the conclusion for part C? There's a lot of ways to put it, but how the answer key puts it, which I think is just fine, is that the angle of depression from the hot air balloon gets smaller as the horizontal distance increases. And again, I think the most intuitive way to understand it is think about extremes. See? Think about you being super close to your friend on the hot air balloon, being right on top of them. You are staring straight down. Now imagine that you're super far away. Well, you're not looking straight down. In fact, you're almost looking straight ahead, ¿cierto? It just has a little bit of an angle. So, ladies and gentlemen, that would be for number 2. All right, and now for this third one, we have that on the 1st of January of 2022, Mina deposited 1,000 into a bank with an annual interest rate of 4% compounded monthly. At the end of January, at the end of every month after that, she deposits $100 into the same account. And for part A, we need to calculate the amount of money in her account at the start of 2024. Give our answer to 2 decimal places. All right, you guys. So this is clearly a finance problem, okay? And you, in pretty much all of the tests I've seen lately, you have at least one of these per test, okay? And so for the finance problem, you have 2 main tools, okay? You have in your formula booklet, okay? Formula booklet, you have this formula that you can use. And also in your calculator, you have the finance app, okay? Now, I need you guys to have the following intuition. See? Whenever you have something where she deposits 100 into the same account every such and such amount of time, you're going to be using the finance app. Okay? If that is not the case, okay, if you have like, for example, if the exercise was this, if the exercise was just this, then you would be just fine using the formula booklet. Okay, and that is something that I need you guys to understand right off the bat. Because even if we use the finance app, it uses part of the formula booklet just with this added thing. And it's important to understand like what it's doing. Okay? Anyways, in the formula booklet, it's important to get familiar with it because the day of the test, you're going to be walking with the formula booklet, the calculator, your pen and pencil, like 30 minutes of sleep and your energy to do well. And so part of what your formula booklet has, okay, important to get familiar with it because it's a tool the day of the test, is this thing called compound interest, okay? Which is exactly what's happening here, see? So compound interest, see how here we're calculating the amount of money in her account at the start of 2024? Well, what is the date where she deposited her money? January 2022. And so there's a bunch of money she got in between those 2 periods of time, okay? Through what? Through interest. Okay, so there's this compound interest formula to help us see how much more money she has earned, okay? How much money she has earned because of the bank, whatever, okay? So here's my compound interest formula. So as you can see, it has 5 components, okay? And for these exercises, if you can fill in all 5, just use this, okay? So FV is future value, PV is present value, N is the number of years, K is the number of compounding periods per year, and R is the nominal annual interest rate, see? Now, we're going to be able to find almost all these things except for the fact that she deposits $100 into the same account, see? But it's still important to look at it from the perspective from the booklet because it helps you define FV, PV, and all that stuff. Okay? So. Point is, future value, the money she's going to have in the future. See, is that something I have? So FV is actually what I'm missing. See, we need to calculate the amount of money in her account at the start of 2024. We need to calculate her future money. Okay? PV is the present value. So present value, what did she deposit initially? She deposited 1,000. Okay, now we're getting somewhere. N is the number of years. Okay, so, or better said, okay, in the context for the finance app, it's not exactly number of years. It's more like the amount of periods, okay? So because we have this thing that is monthly, okay, how many months is it from January 1st, 2022 until January 2024? Well, it's 2 years. How many months does a year have? 12. So 2 times 12 is going to give you 24. Okay, so N, which I know the formula booklet says years, but in this case, we're going to be working because of the finance app. Okay, N is going to be like amount of periods, N is going to be 24. Okay, you have 24 months between 2022 and 2024. All right, cool. What else do we have here? We have K is the number of compounding periods. So this is going to be relevant. It's not exactly what we're going to put into the finance app, but because it's monthly, how many months do we have in a year? 12, okay? And last but not least, we have, it asks for the nominal annual interest rate. We have R, so R percent. They tell us that it's 4% compounded monthly, see? So right now, we are from the perspective of the formula booklet, and we're going to bring it to the finance app in the calculator, okay? I just think it's more intuitive to approach it that way, okay? To each their own, but whatever. So we need to calculate FV knowing this information and the fact that she deposits $100 every month. Deposits, deposits, deposits. And the fact that she deposits $100 every month. So let's see how my calculator is going to help me with that. So as I said, we need to use the finance app. And so of course we click this purple button that says apps and go to finance. Okay, some calculators have a little bit different. This is the one we're going to be using ourselves. So here we have this thing called TVM solver. Now I was already playing around with it a little bit earlier for this exercise. But oops. Well, let's just imagine we have everything like just sort of empty, okay? Yeah. So as I said, N is the amount of periods, see? And so because from January 2022 to the start of 2024, we have 24 months, and we're talking about months, N is going to be 24, okay? I, as you see, is in percent. That's going to be the interest rate that we're working with. In this case, it's going to be 4%. So I'm just going to put 4. PV, present value, 1,000, okay? And here is something important that we have to keep in mind, you guys, okay? The symbol for PV, like positive or negative, and the symbol for PMT has to be the same. All right, just stick with that intuition, see? It makes a little more sense if I say negative 1,000 and negative 100. Now, PV, as I said, is the money she invests initially, okay? And PMT is this thing down here. If she deposits $100 every month, your PMT is going to be 100, okay? That is intuition for PMT. All right, so why would it be negative? It's negative because from the perspective of Mina, how much money did she lose initially? Well, she lost 1,000 because it's what she deposited. She's going to get a lot more later, right? But it's what she lost initially. So negative 1,000, negative 100. FV is actually what we're looking for, so we're just going to leave it empty. And PY and CY, just stick to the idea that it has to do with whether it's yearly or monthly or whatever for the annual for the interest rate that is compounded. See? So keyword here, see how it says compounded monthly right there? So if it's compounded monthly, it's how many periods? It's going to be 12. So because it's 12 for P over Y, we're going to put 12, and C over Y, we're going to put 12 as well. Okay, so this has to do with the fact that it gets compounded monthly 12 times. See? That is the number of your compounding periods. Compounded monthly, you put 12. See? If it would say compounded bi-monthly, you would put 6 because you have 6 bi-months per year. See? Anyways, as you can see, if you change one, the other one changes according to it. So if you put PY is 12, CY changes immediately. See? That's fine. We have everything written down. Now we just need to put your FV. Okay? Also, for PMT, I'm going to work with end. You can do it with begin. but just stick to one version, okay? Like whatever floats your boat, stick to it. I'm gonna stick with, and that's how I'm gonna do it, whatever. So as you can see, I have everything except FV. And so the way to find out what FV is using this thing called solve, okay? So you see how this enter button in green has solve? So whenever you want to press a green button, well, you press your green button here, alpha, and enter, and that lets you hit solve. So if I press solve over FV, what it's going to do is that it's going to take all these other values and find what FV is. Okay, intuitively, you can say like, so it's filling in this guy, it's filling in this guy, this guy, this guy, this guy, and the PMT, and it's going to give you FV. So if you solve for FV, it plugs in everything else and finds what FV is for you. Okay, this is especially useful when, let's say, you're trying to find something that is on an exponent, like n. See, getting n alone is super hard, so the solver works great. Okay, whatever. So I'm going to go ahead and, as I said, press alpha, enter for solve, kapow. It gives you that value there. That is the answer for part A, actually. So for part A, you're going to go ahead and put that the answer is 3.577, comma 43. Well, FV, see, in dollars equals this guy here. That is for part A. Again, very straightforward, very quick. I just did a lot of explaining because some of you probably didn't know what PMT was. Maybe you didn't know why it was negative up here. It's from the perspective of Mina. Okay, so from the perspective of Mina, she lost $1,000 initially. She's losing $100 every month. Okay, you can do it in the version where they're both positive. Okay, and do the solver here, and you're gonna see that you get the same value, but it's negative. Okay, and so then you would have to flip the perspective. You see, it would be like, I don't know, perspective of the bank or some shit like that. Okay, whatever. For me, it's a lot more sensitive. I make it from Mina's perspective. She loses $1,000 initially. She loses $100 per month. So that means that my future value, what I earn, is going to be that amount. Okay? Whatever. That is part A. For part B, we need to find how many complete months from the 1st of January it will take for Mina to have more than $5,000 in her account. See? So, in other words, what's happening now is that because we need to see how many more complete months, how many more complete months is which variable? Is it PV? Is it N? Is it FV? Is it K? Remember that N is like the amount of time, okay? And in the formula booklet, N tends to be in years, yes. But in your finance app calculator, N is whatever you're working with. So in this case, we had months, so we put N equals 24. In this case, because we need to find how many complete months, this is now what we're trying to find. So this is now X, and because they tell us that it has to be having more than $5,000 in her account, it's whenever FV passes 5,000, okay? Whenever FV passes 5,000. So if I go into my calculator, I'm going to put FV as 5,000, and N is actually what we're trying to solve, see? So now everything else stays the same. All I changed was FV and N. I'm going to use solver for, sorry. I'm going to use the solver for N to find how many complete months. So alpha, enter for solve. There it is, see? So for part B, you would put 36.4689. Oh shit, 36.46869. God, why does that look so nasty? 36.4689. Okay, so this is the amount of months, right? Now, because of the context of the problem, okay, you can't work with half a month, okay? Why? Because, and here's a big hint, it says, boom, it says complete months, okay? So you can't work with half a month. So basically, what the exercise is telling you is like, okay, after how many months does she have more than 5,000? Okay, not half a month, not half a week. After how many months are you sure she has at least over 5,000? And so because it's at 36 and a half, if you say 36, you're actually going to end up with a little bit less than 5,000. See? In fact, if I put 36 here and I use a solver for FV, we're going to see that I'm a little bit below 5,000. See? And so the moment that you put 37 for your amount of months and you solver down here, now you're over 5,000. See? So you're going to pick 36 or 37. 36 is not enough, so it has to be 37. When is it enough? When it passes 5,000. Okay? That is for part B, ladies and gentlemen. And number 3 is not that hard, but you do have to know what the hell is going on with the calculator. See? So again, the biggest intuition I can share is that PV and PMT share their symbol. Share the symbol, okay? I suggest putting it in negative because it's from the perspective of the person investing. So she loses, Mina lost $1,000 because it's what she invested initially, and she loses $100 per month. So that's why it makes sense to put negative 100, I mean, negative 1,000 and negative 100 for both. See? Regardless of the way you approach, make sure they share the symbol, okay? The second thing I can say is that PMT is for the monthly additional, okay? Is for the monthly additional, all right? The other thing that I think is important is that N, although the formal booklet says it in numbers of years, for the finance app is just like the number of periods, okay? So if you're working with months, you would have 24 periods, okay, for part A. For part B, it ended up being 37 months, so N was 37. If you have those two things in mind, it's fairly straightforward, you guys. It's not that hard. And you just gotta know what the calculator, how it works, what it asks for, and stuff like that. So I hope this exercise assisted you in that, cierto? Regardless, I wish you the best, and that is number 3. Okay, and now for this fourth one, we have that carries believes that on a memory retention test, the mean score of bilingual people, UB, bilingual, B for bilingual, will be higher than the mean score of monolingual people, UM, for monolingual. Okay, so Carries gave a memory retention test to a random sample of students in her class. The results are shown in 2 tables. So as we can see for memory retention, the first bilingual person scored 100. The second bilingual person scored 94%. The last one scored 98%. For the monolinguals, we see that the first monolingual scored 97, the second one 92%, the third one 88%. Okay, that's the information we have at hand. That is the context. Carries then performs a one-tailed t-test. Okay, that's a lot of information. At a 5% level of significance. Damn, that's even more information. It is assumed that the scores are normally distributed. What the hell is that? And the samples have equal variances. What the heck is variance? Alright, so some of you probably have a couple questions of what the heck is going on. So, let me give it to you straight. This person Carries, okay, is seeing who has better memory. Bilingual people or monolingual people, okay? And so one of the ways that you can like mathematically prove that, okay, is seeing if the means of each of these two are different. Let's remember that the means is the average, okay? A mean is also like an average, yeah? Oops. So if on average, let's say the average of bilingual, I'm making this up, okay? The average of bilingual is 99, and the average of monolingual is, I don't know, 70, then there's, it seems to be, right, that bilingual people do like way better in memory retention than monolingual people, okay? That's what you would think looking at the means. But to further prove that, there's this thing called statistical significance. Okay, so basically what you're trying to do very intuitively is that you make this sort of test that compares the means. A t-test is for means, by the way. Okay, whenever you see t-test, a t-test is for comparing means. And so you compare the means at a 5% level of significance, which is basically like how much you're asking of the test. So the lower level of significance, the more the more exigente, the more you're asking of the test, okay? So basically, it's a sort of test. It runs like a couple, regressions or whatever. I don't want to get into it. I don't know it 100% well, I'll be honest. But the intuition is that you run a t-test, it does like a bunch of samples, and it sees if it's significant or not. It sees if this difference right here is like legit or not. See, because it could have been chance. It could have been chance that, oh, of the people you picked, there's a difference, but it's not always going to be that way. Whatever. Okay, so the level of significance helps you figure out if the difference you have is significant or if it's just by random chance that you have that difference. So, it is assumed that the scores are normally distributed. When you have data and statistics, it can have a lot of different distributions. Okay, and that distribution is a little bit of how your data is like spread out, how it looks like, stuff like that. When it's normally distributed, we have our classic sort of bell curve, okay, where you have your mean in the middle and you have like standard deviations 1 over, right? Standard deviations 1 back, and a bunch of stuff, okay? So this is one way your uh, distribution can look like. You also have other distributions that might be like a little skewed. Maybe other ones are skewed over on the other side. Whatever, okay? So normally distributed, it's like your classic case, your friendliest case. And now they tell us that samples have equal variances. Now, I'm sure some of you don't have the intuition of what a variance is, okay? Variance, I want you to have in mind that variance is basically a little bit like spread of data. See? Standard deviation is also deviation. How the hell do you even write that? Standard deviation is also going to be spread of data. Okay, there's a slight difference between the two. One of these is squared, the other one's not. Okay, and that has to do with handling negative values. Okay, but for our level, for the IB, AISL, just stick with the intuition that variance and standard deviation is spread. And so here, when they tell you that they have equal variances, all they're telling you is that their spread is the same. Okay, and because their spread is the same, and this is the sort of thing you memorize, because their spread is the same, because they have equal variances, you pretty much are you're gonna say that it's pooled. Okay, when we use our calculator and in the data section, in the t-test section, if it's pooled, you're gonna say yes. That has to do with variances. Okay, if the variances are different, they're not gonna be pooled together. But that'll come into play a little bit later. So that's the context of what's going on. See? And so here for part A, we have the null and alternative hypothesis of the scenario. Now we need to understand that this depends on how you define it. Okay, a lot of times the null hypothesis and the alternative hypothesis depends on how you put it. Actually, in the answer key, it says like you gotta be consistent. You gotta evaluate consistently with how they or the student define their own hypothesis. But take it easy. Let's take a step back. What's the intuition? The null hypothesis is what they call the H0. Okay, the alternative hypothesis is what they call the H1. And the intuition that I want you to have for this, or that I suggest, okay, is that for null hypothesis is basically that nothing changes. For the alternative hypothesis is that there is a change. There's a change, there's a difference. Nothing changes or no difference, okay? Basically, I want you to associate null hypothesis to no, and alternative hypothesis to something is different, okay? So, in this context, Caris believes that, blah, 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 the mean score of bilingual people will be higher than the mean score of monolingual people. What's the keyword here? Higher, okay? So the null hypothesis in this context, we would say, for H0, we're going to state that the mean score of bilingual people is the same as the mean score of monolingual people, okay? So that's how you would define H0. If you want to put it in math terms, your H0 would be that the mean of bilingual, ¿cierto? So UB, which is this UB here, equals UM, which is this UM here. This U is for mean, okay? Mean equals this U. You're also gonna see that mean is x with a little bar on top, okay? But in this case, we're applying that mean as u. All right, fuck it. So that is for h0. See, so if h0 is that nothing changes, no difference, so that means that we have the same score. For alternative, you can guess what's gonna be. It's gonna be literally like pretty much the same, just that instead of h0 we have h1, and instead of same we have that the mean score of bilingual people is higher than the mean score of monolingual people. So what's the key difference here? Here we have higher. Okay, that's all there is to it. See, h0, no difference, nothing changes. h1, there is a change, there is a difference. See, so for h1, we're gonna go ahead and say that in line with that Carries believes that the score of bilingual people will be higher. So that means that UB, the bilingual people, is gonna be higher than those of monolingual people. So that is for part A. For part B, we need to calculate the p-value for this test. Now, there are a lot of different tests we can do, but this exercise is pointing us towards one. They literally tell us in the exercise, that we're making a t-test. One-tailed t-test. 5% level significance. That's all we need. See? Well, and these tables here. So, I pull up my calculator, and I know I have to do a test. I know statistics. I'm not sure where, okay? But I've gotten familiar with my calculator. I've practiced a lot, and I know some of the tools I have. So, I know I gotta go to stat because it's statistics. And from here, I have 3 tabs. I have edit, calculate, and test. So I scroll around for a little bit, and I notice that, of course, the last one has tests, and I need to conduct a t-test. So here, a lot of people say, okay, the first one is z-test, the second one is t-test. Oh, fuck it, t-test, see? And then they press the second one. Why is this a small mistake? Think about it. Why is that a small mistake? It's a small mistake because how many groups do I have? Ah, I've got group 1, which is bilingual, and I have group 2, which is monolingual, okay? So that is why, if I go back to the same menu, I have to go down to 2 sample t-test, okay? I have 2 samples, I have 2 groups. The first group is bilingual, the second group is monolingual. So I press the 2 sample t-test. I see what it asks for, see? On the one side, I can input data or I can input stats, all right? If you input stats, you're doing it all by hand. I don't think you ever really use this, so like forget about it, see? Basically, you enter the mean yourself, you enter the the variance yourself, the standard deviation yourself, the n yourself. You could do it that way, but you take a million more years, and I don't think you're ever gonna have to do it. So just go ahead and go to data, see what it asks for. All it asks for is list 1, list 2, frequency list 1, frequency list L2. These last 2 things, I'll go over it in a second, see? But for like data-wise, I just need to fill in my lists. So how can I reach list on my calculator? Well, I go to stat because it's a stat problem, and I go to edit because I gotta edit some lists. Boom, there are my lists. Here I have L1, here I have L2. So go ahead and delete all of these. So you can go one by one if you like to do that. So you delete, delete, delete. Or if you want to do it a little quicker, you can go up top to where it says L2, clear enter, boom, clears it all for you right away. So that's just a quick math trick, quick calculator trick. So group 1 is going to be L1, group 2 is going to be L2. Bilingual L1, monolingual L2. Cool. So I literally put in the list that I have there. So it's 194. So this 100, this 94, this 100, this 90, this 100, this 90. And now you guys know what's going on. See, so 100, 94, 98, 98, 98, 98. So that is all the rest of these, okay? For monolingual, go ahead and plug in 97, 92. So that's these 2 here. Then we have 88, 98, 88, 94. So that's these next 4. Then the last 200 and 100. 100 and 100. Compound, compound. Some of you might be thinking, yo, my data is not aligned. Like, there's more data on L1 than L2. And I would say, yeah, you're right. That can happen. It's okay. Not a big deal. See? Stat, test, 2 sample t-test. I already put on my data. So here, list 1, list 2, I am good to go. Frequency has to do with if this were to have a frequency list, okay? And just to clear this up, because I know some of you are probably like a little bit confused on what that means. For example, if I were to express this first one in a frequency list, I would have, well, I have bilingual, ¿cierto? So bilingual people. I would have score, and here I would have frequency, okay? And so the way that works is that, let's say for score 100, how many people that are bilingual scored 100? So I have 1, 2. How many people that scored 98 are bilingual? 1, 2, 3, 4. How many people? Oh shit, I missed 100, sorry. Frequency 3, I missed this one here. What about 94? For 94, we have 1 and 2. And for 90, we have 1, okay? So if you were to do it with a frequency list, okay, it would be a little bit like this, see? And your frequency over here would probably have to be one of the L1s. So you would say like all of this is L1, all of this is L2. It would be a little bit different, okay? Usually you're not gonna face that, but I think it's good to know what's going on, what's happening, etc. See? So all my data is now aligned, right? For this last part, it's a little bit like it's your alternative hypothesis. Okay, this last part here is literally your alternative hypothesis. So my alternative hypothesis was that UB, right? UB is greater than UM. Now I have to be consistent. See, which one of these is L1 and which one of these is L2? Careful, which one is L1, which one is L2? Well, because I wrote it down on my paper and I was consistent and I was careful, group 1 is L1, group 1 is bilingual. So basically this here for my alternative is the same as L1 being bigger than L2. Well, and technically given the context is that the mean of the first one is bigger than the mean of the second one. And so keeping that in mind, I would have to press this third one here. See? If I press the first one, I would be saying this, which is not the case. If I press the second one, I would be saying this, which is not the case either. If I press the third one, it's literally what I want. It's this, which comes from this, okay? And then they ask us if it's pooled, and I'm just gonna say right away, guys, you pretty much always put that it's pooled. Yeah, I don't think I've seen in a while an exercise where you put that is not pooled. Put it pooled if the samples have equal variances, which is pretty much always. So just leave it as yes. You calculate, you end up with a bunch of shit. See? So let's go ahead and try to identify what's happening here. So I'm just gonna say right away, the t-value, okay, so see how I have a t equals of 1.22 and I have a p-value of 0, 1, 19, 0, 119, sorry. 119. So I don't want to get too into it because I know statistics can be really fucking weird. But point is, this t-value and this p-value can help you conclude the test, okay? And depending on what you compare it to, you either use t-value or you use p-value, okay? In this case, because we have a level of significance, we will be using our p-value, okay? That's literally it. So that's the information it gives you. DF is this thing called degrees of freedom, okay? It doesn't really matter. Forget about it. You barely use this, okay? X1 and X2 with the bar is the means. The S's, I'm pretty sure are variances, see? And then we have the variance that's pooled, okay? I think so. I'm pretty sure. Yeah. See, don't worry about it. N1 and N2 is the amount of data you have, see? Whatever. A bunch of shit shows up in your calculator. The only thing you really care about are the first two, see? The t-value and the p-value. And so for part B, the value of P for this test is literally right there. So part B is this. Kapow. Not that bad, eh? Not that bad. And now for part C, we need to state the conclusion of the test in the context of the question. All right, so how do you interpret this? And again, this is very much like sort of like a rule of thumb, okay? If the p-value is bigger than your level of significance, when I say level of significance, it's this guy here, okay, 5%. If the p-value is greater than the level of significance, notice the language. You fail to reject HO. You fail to reject HO. And in very, very fancy math language, you would say that there is, because p-value is greater than level of significance, there is insufficient evidence to suggest that bilingual people have better memory retention than monolingual people. Okay? That is the very fancy math way to put it. This is also literally like from the answer key, okay? But yeah, that's what you end up with. See? And so notice how this p right now is in decimal. See? So I can either say that 0.119 is greater than this 5%. See how to express 5% in decimal, 0.05. And so that is what tells me that I failed to reject HO. If you want to express it in percents, you would have 11.9% being greater than 5%. Okay? Either of these works. Both are in the answer key. Stick to what floats your boat. See? But yeah, that is pretty much it. So for part C, that is what happens. See? This is one way to define it. You can define it however you want. Um, but the very key information is that you put that you failed to reject HO because of this guy here. See? Again, this is sort of thing you just kind of have to memorize. You can end up learning it, but for now, stick to it intuitively, okay? If p-value is greater than level of significance, fail to reject. And always define it the same way. Because technically, you could also say here that you accept HO, see? And some people like to think about it in terms of accept. Other people like to think it in terms of failing. But then this is also double negative because it's fail to reject. So it's a little bit confusing, guys. All I'm saying is stick to whatever helps you understand it better, okay? But anyways, that is parts A, B, and C, and that is for number 4. All right, so for this fifth one, we have that line L1 is tangent to a graph of a function f of x at the point 3, negative 1. Line L2 is given by the equation blah. Okay, so all of this is L2 and is perpendicular to L1. Okay, so there's a lot of buzzwords going on. Let's see what's happening. So for part A, we have to write down the gradient of L1. Ooh, look at that, another buzzword. See? So let's go bit by bit. Okay, gradient, all right, is the same as slope. Okay? And in your formulas, you're going to see that gradient is actually what they call m. Okay? And if you go into the formula booklet and you look for your gradient, there it is, the gradient formula, m equals blah. See? So just so you know, I'm taking this from the formula booklet, okay? From the formula booklet, we have that m equals y2 minus y1 divided by x2 minus x1, see? Now the slope of anything, okay, is basically its rate of change, see? So if you have a line that looks like this, okay, kapow, its slope is going to be, well, what's the distance from this point to this point? That is your slope, okay? Now, see what I just drew. On the one hand, you have the thing in green, which is kind of like this y2 minus y1, okay? And on the other hand, you have what I'm putting now in, let's say, yellow, okay? And in yellow, we have the part of x2 minus x1. Okay, so basically what I'm trying to tell you is that for calculating your slope, okay, your your gradient, you are seeing the change in horizontal. You're seeing the change in vertical because your y values are your vertical divided by the change in horizontal, okay? Because your x is your horizontal values, all right? So that's just a little bit of a chit chat about what gradient is, what slope is, okay? When we have lines, there are different kinds of slopes that can appear, okay? If you have what we call parallel lines, okay, this would be a case of parallel lines. All right, this is parallel. Why is this? That is a P, not an R. This is parallel because the first slope of the first line is equal to the second slope of the second line, okay? These are lines that will never touch because they're parallel, okay? If they were just a little bit different in slope, okay, just a little bit different, eventually they would touch each other. See? Way down the line, but they would. Okay? So when they're parallel, they never touch. Alright? This is a case where they're almost parallel, but as long as they're not parallel, they're gonna touch eventually. Okay? Whatever, fuck it. You have the case of parallel lines up here. See? The case of perpendicular lines, which is what this exercise has, is when it looks like this. Kapow, kapow. Literally, okay? You're gonna have the first line here, the second line here, okay? What is happening in this case? Well, as you can see, one of them is sort of like the inverse of the other, okay? So if for parallel, if for if for parallel we had that the first slope is equal to the second slope, for perpendicular, which is what I drew just now, you're gonna have that the first slope times the second slope equals -1. Okay? And I know that this for some people this is like good enough, and for the other people they're like, what the fuck is going on? So a better way to understand it, in my opinion, is that perpendicular slopes is you flip it. So you're first gonna flip it, and then you're gonna multiply by -1. For example, for part A, here you have this line, ¿cierto? The line of the equation, y equals blah, blah, blah. See? The line of this equation, so y equals -1/2 x minus 5 over 2, because it's a normal line, okay, it's not a parabola, nothing weird, because it's a normal line, it comes from this world. It comes from the world mx plus b. What do we know about this line? We know that b is the y-intercept, and we know that m is the slope. So, if this is the slope of L2, see? And we know that L2 is perpendicular to L1. How do I find the slope in L1? Well, because they're perpendicular, I flip it and I multiply by -1. So I'm going to take this -1/2. I'm going to flip it. So the first I'm going to flip. Okay, here's the flip. Da, 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 da. Flip it. And then I multiply by -1. So if I multiply by -1, it's going to look like this. I end up with 2 over 1, which is just 2. Okay? So intuitively, you can remember that you have to flip it and then multiply it by -1. If you want the math answer, you can see it here. So if m1 times m2 equals -1, that means that m1 is equal to -1 divided by m2. And so see how m2 is on the bottom now, that is the flip part. And see how there's a -1 up here, that is the multiply by -1. Okay? Anyways, fuck it. For perpendicular slopes, okay, you flip it and multiply by -1. So let's do another example. Let's say that your slope is -4. And I say, yo, this is the slope of L1. L2 is perpendicular. So if the slope of L1 is -4, the slope of L2 is going to be 1 over 4. What if I tell you it's 2 over 3? For L2, it's going to be -3 over 2. What if I have, I don't know, -69 divided by 420? Well, I'm going to flip it, times it by -1, ends up being positive. See? So really look at these 3 examples, really try to absorb it, and you should be fine. Okay, if you understand these three, you understand particular lines. See? Rule of thumb, flip it, multiply by -1. You should probably write that down somewhere. See? Anyways, whatever, that is part A. So for part A, you literally just put this m1 to show that the slope of the first one is going to be 2. Let's move on. For part B, we need to find the equation of L1 in the form y equals mx plus c. Remember how I wrote mx plus b? Sometimes they write mx plus c, okay? The idea is the same. This is still the y-intercept. This is still the slope, okay? Anyways, for part B, what I suggest is this fancy line that I'm pretty sure is in your formula booklet. Let me just double check. So here I have, oh, actually here it says, so equations of a straight line, right on top, see? There are three ways to write the equations of a straight line. You have the first one that I showed you, okay? You have this one in the middle, which is kind of weird. They usually ask for the answer in this form. And you have this one, this last one. Okay, this one is the most useful, okay, in my opinion. This is what they call point slope form. Now, guys, I need you to keep this in mind. It's super important, so I'm going to slow down. Point slope form is what you're going to use to start your exercise, okay? From point slope form, you can go to this very easily, and you can go from here to here very easily, okay? Technically, you can go from any of them to any of them, okay? But point slope form is particularly useful to go from this form to this one, okay? So use point slope form for what? For starting, ladies and gentlemen, see? So let's go to part B. Let me make a little bit of space because I did a lot of chit chat in the beginning, although I think it was useful chit chat, but that is for you to decide. So for part B, what do we know? So first of all, we know that, what do we know about L1? So we know that L1 has the slope from part A of 2. What else do we know about L1? Tell me. Take a second, read what we have. What else do we know? There's got to be something else. See? Ah, L1 is tangent to the graph of a function at the point 3, -1. Some of you are probably thinking, what the fuck is a tangent? So, let's say you have a parabola like this. Okay, so this is my parabola f of x. See? I can have, let me just, whatever. It looks like this, okay? And let's say that at x equals -2, okay, I'm just making this up. At x equals -2, we have a tangent. So a tangent is a line that touches my function once and never again. Okay, so usually it looks like this. It touches here and never again. See? I can have a tangent, let's say at x equals whatever, 3, okay? And it would probably look like this. It's going like this, going like this, going like this. Boom! Barely touches right there. See? That would be another tangent. Okay? So that is the idea of a tangent. Touches once, never again. Touches once, never again. So, why is it useful that L1 is tangent to the graph of a function f of x at the point of 3, -1? Well, think about it. At 3, -1, conveniently I put it right here. Okay, this is a made-up example, by the way, see? But there is something important to notice here. So, at 3, -1, L1 is passing through 3, -1, and f of x as well. So, what am I trying to say? It is, ladies and gentlemen, a point that they share. So if it is a point that they share, it is a point that they both have. Ah, okay. So what you're telling me is that L1 basically has the point P, 3, -1. That is what it's telling me, okay? The tangent thing might be relevant later, but for now, this is all we know for part B, and it is also all we need for part B. And you're gonna see why in a second. So let me leave this over here. It is a point that they share. See? So, as I said, point slope form is what you're usually going to use to start these exercises. Okay, so point slope form from the formula booklet, this last one looks like this. We will have that y minus y1 equals m parentheses x minus x1. So, what do I need to fill in to use this? I need to fill in y1, x1, and m. Y and x are just variables. See? It's no different than this y and this x. See? So, this x1, y1 is just a set of points. Literally, okay? If you ever face something that says x2, y2, that makes reference to my second set of points, okay? Notice how this 1 goes with this 1, this 2 goes with this 2, okay? As long as you're consistent with that, you are doing things right, okay? So, whatever. Point is, this little one and this little one here are telling me that they're the x's and the y's of the same point. And so in this context, because I have the point P 3, -1, x1 is 3, y1 is -1. M is 2 because I got it from part A, and I can now plug in. So I'm going to have y minus 1 equals 2 parentheses x minus 3. Notice, just a quick comment some of you could really use. Here, I plugged in parentheses, okay? Ladies and gentlemen, always plug in parentheses. The reason it is worth it to get used to plugging in parentheses is that way you avoid the problem of the double negative, okay? For me, it's much more apparent that there's two negatives here when I plug in with parentheses. If I were to not plug in parentheses, something we've probably all done, I might have just plugged it in like this. I literally might have just done that, okay? And so to avoid that issue, make sure you plug in parentheses. See? Just a quick comment, might be useful, fuck it. So on the left side, I end up with plus 1. On the right side, I end up with 2x, because I multiply like this, minus 6. So y equals 2x minus 1 minus 1. Careful with the negatives, -7. That is part B, literally. And now, last but not least, for part C, we have that show that L2 is not the line that is normal to f of x at point P. Ladies and gentlemen, there's probably 90% of you that are thinking, what the fuck? What? I mean, what? What do you mean normal? What's happening? Say? Guys, I got it. So, remember how I said that you can have a line that is tangent. See, so let's say you have this parabola, you have this guy here that is tangent, okay? So the scenario where it's tangent, okay? The scenario where it's tangent, you have the slope of the first line, okay? The slope of the first line being equal to the second line, see? When you have a normal, I'm going to put it in red, when you have a normal, the slope of the first one is equal to the slope of the second. I'm not sure why I put an L there. When you have a normal, the slope of the first one is perpendicular to the second one. Okay, when it's a normal, the first slope is perpendicular to the second one. So a normal would actually look like this. All right. Let me just put M3 here so that we understand we're talking about L3. Okay. So just following my example, like whatever, fuck it. When it's tangent, the slopes are the same at that point. Okay. When it's normal, the slopes are perpendicular at that point. Okay. Whatever. You got it. So you can sort of associate tangent to like parallel because the slopes are the same, and the normal to perpendicular. See? Maybe that helps a little. And yeah, what's the key difference between these two? Well, that the tangent is at that point the same slope, and that the normal is perpendicular slope at that point. See? All right, cool. So for part C, show that L2 is not the line that is normal to f of x at point P. So, what can we do? There's a couple of ways to really sort of approach this, okay? The first one we can do is that we can consider point P, see? And so the first thing we can do is seeing if point P, okay, is in L2. If point P is not in L2, then L2 has nothing to do with it, see? Let's see what happens. So L2 is this guy here, see? So L2, we know, is y equals negative 1/2 x minus 5 over 2, see? We know that point P is this one here, 3 comma negative 1. So let's go ahead and plug in. See, so if I plug in P, I end up with negative 1 equals negative 1/2 times 3 minus 5 over 2. In other words, negative 1 equals negative 3 over 2 minus 5 over 2. What is this telling me? It's telling me that negative 1 has to equal negative 8 over 2. What does this mean? That negative 1 equals negative 4. Guys, there ain't no trick here, okay? Does negative 1 equal negative 4? No. 1 apple does not equal 4 apples. So what you can say as an answer, literally, is that L2, and this would be your answer, L2 doesn't have the point P, so it can't be the normal line. Because it doesn't even touch. I mean, it can't even be tangent because it doesn't touch it. See? That is the main method you can try to do. Okay? There's a couple other methods, but I don't think it's worth going into them. I'm just going to leave you with this tool. Okay? If you plug in P and you get something weird like negative 1 equals negative 4, it's not part of the line. Don't worry about it. Okay? There's two other methods. You can check for the answer key in a bit. But basically, stay with that. Okay? You can attempt to show that P doesn't lie on line L2. You can attempt to find the equation, but that is a little more annoying. And intersection is a little easier, but still. Okay? Stick to the most intuitive one. Okay? I'm not going to show you all the tools because you guys don't need, I mean, ideally you have all the tools, but guys, I'm just trying to explain this one problem. Okay? For this one problem, the most direct approach is plug in P. If it doesn't work, move on. Okay? L2 is not the normal line at LP because it does not lie on L2. See? This is no different than what I told you just now. Okay? I just told you that L2 doesn't have the point P, so it can't be the normal line. What's happening here, if you're still not convinced, what's happening here is that you have the line f of x. Let's say it's something like this. Okay? Let's say that this is f of x. Okay? And let's say that I have my line, I don't know, L2 that goes like this. Okay? What we're saying is that, yo, at 3 comma negative 1, which is here, L2 is the normal. And it's not, because at L2 doesn't even touch f of x. Okay? Even more, what's truly happening, sorry, I actually messed up here. What's truly happening is that the point 3 comma negative 1 is this one. And so 3 comma negative 1 doesn't even fit in L2. Okay? If it would have fit, then you need to see the slope and see if it's the same slope as f of x. Okay? In this case, it doesn't even, this point doesn't belong to L2. Okay, so if it doesn't belong to L2, we don't care about it, fuck it. Alright, this last explanation was a little long, but although I did do a lot of blah blah, I covered all things and I'm sure it helped. See? So anyways, I hope it helped. I'll see you around. Moving on with number 6. Alright, so for number 6, okay, we have that when the brakes of a car are fully applied, the car will continue to travel some distance before it completely stops. Alright, yeah, that's true. This stopping distance, d, in meters, is directly proportional to the square of the speed of the car. V in kilometers per hour. Kilometers times hour to the power of -1. Guys, when I hear kilometers per hour, I'm very used to seeing kilometers per hour. Okay, it's the most usual way to express it. Now notice, here it's a division sign, right? km/h, which is the same as me saying kilometers divided by hours, which is the same as me saying if I want to put h on top, because it's an exponent, I would put h to the power of -1. Okay, so whenever you say h to the power of -1, it's really just saying that. All right? I don't know, just some people have that question, might as well answer it right away. So they tell us this piece of information: when a car is traveling at the speed of 50 kilometers per hour, it will travel 12.3 meters after the brakes are fully applied before it completely stops. So for part A, we need to determine an equation for D in terms of V. Now, you guys, this exercise is really fucking weird. Okay, I'm just gonna be straight up. I don't find it completely intuitive. It's like that one exercise in the test that's just kind of like, huh? Like, really? Just the first part of the exercise is like fucked up, and then everything else that comes is way more intuitive. Okay. Point is, they tell us this relationship. They tell us that the stopping distance d, okay, in meters, is directly proportional to the square of the speed of the car, v. Okay. So what a lot of people do here is that they say, okay, so d is directly proportional, right? So it equals to the square of the speed of the car. So square of the speed of the car. So speed of the car squared. Okay, a lot of people write it down like that, and they're like, okay, I'm good to go. And then they do the whole exercise, and they only get half credit for everything because there's an error. What's the error? How can you check for the error? So here it says that when a car is traveling at the speed of 50 kilometers per hour, it will travel 12.3 meters after the brakes are fully applied before it completely stops. So that means that D is 12.3 and that V is 50. So if equation A is completely correct, then it should work, right? Okay, so 12.3 for D equals 50 squared. Do you guys think that's true? So 50 squared, I did it earlier, is 2,500. So 12.3 equals 2,500. Guys, is this true? No. 12.3 does not equal 2,500. So what's going on? The thing that's happening, and this is the part that I don't like about this exercise, the thing that's happening is that, okay, yes, the distance is directly proportional to the square speed of the car, but there's something else going on as well. Okay, it's not just the speed of the car. There is something sort of like unexplainable going on. So I have this constant k that explains that thing that I don't know what's happening, and I still have my velocity squared. Okay, so my new equation now looks like this. All right, we have 12.3 equals this k that I put in there times 50 squared. And so my sort of real equation is one that explains that big difference. It's this sort of constant that helps you figure it out better. Okay? So what's the intuition I can share? Well, if you plug in the values that they give you and they don't equal each other as they should, then your equation needs to be changed slightly. See? Now, because I don't have any further information, all you can really say is that there is sort of a constant being applied to the velocity. Okay? Which actually has to do with part C, okay? Part C, as you can see, it asks for, after the brakes have been fully applied, identify one other variable besides the speed that could affect stopping distance. And so for here, I know it's the last part of the exercise, but just intuitively, context-wise, I don't know, something that can stop the braking, that can change the braking distance is, yo, is there snow on the road, okay? Are the wheels okay? Is there wind? Is there mud? Okay, there's a lot of different reasons that your stopping distance is not going to be like perfectly just the velocity squared. And what does it explain it? Well, all of these reasons here, how do you express them? In this k that's right there. Okay, so that is why putting that k there sort of makes sense. Okay, if k is equal to 1, which is basically like no effect, okay, you're telling me that there is no snow, the wheels are in perfect condition, there is no wind, there is no mud. Like, it's like the classic physics problem where like everything is perfect, you know, like there's no friction, there's no this, there's no that. Here, they don't give it to you right away. You can sort of tell that there's a constant because this here doesn't make sense, right? 12.3 does not equal 50 squared. And so because it doesn't equal 50 squared, then there has to be something unexplainable going on, unexplainable called k. And so now we find the value of k and everything else makes a lot more sense. See? So again, that is a part of the exercise that I think is like very tricky, not very fair, but I was thinking about the best way to explain it, the best intuition, and I think there it is. Okay? So what is the value of k? Well, I'm going to have that 12.3 equals 2,500k. See? Because 50 squared is 2,500. You want to get k alone, right? So k is being multiplied by 2,500. What's the opposite of multiply? Divide, ¿cierto? So divide here, divide here. K equals this, divided by 2,500. Trust me, guys, when I say that k is equal to, or actually, yeah, let's check. So this divided by this. All right, cool. So k equals 0, 0 point, sorry, 0.00492. Okay. So now that I have this value for k, for part A, I can express my answer much more appropriately, ¿cierto? So I'm gonna make a little bit of space because we're probably gonna need it later. But basically, for part A, you're gonna write that d is equal to k times velocity squared. We know how much k is now, so we're gonna put 0,00492. That is my k times velocity squared. All right, and that is part A. All right. So there's my equation for d in terms of v. We figured out we needed a constant because we plugged in this piece of information and didn't make sense. So we needed to find the unexplainable part called k. Then they tell us that the police can use this equation to estimate if cars are exceeding the speed limit. A car is found to have traveled 33 meters after fully applying its brake before it completely stopped. So we need to use the equation from part A to estimate the speed at which the car was traveling before the brakes were applied. Guys, I'm going to say something right away, okay? A lot of you might be thinking, God damn it, I'm not going to realize the day of the test that there's a K. I'm not going to do the thing of plugging in here, I'm going to forget it, and fuck it, I'm going to get it wrong. Guys, you're in this test. You're in it to win it, alright? You might not get it everything 100% correct, but you can still get points for effort. Like literally, there's points for effort here, okay? Look at part B. It says, use your equation from part A. So that means even if your equation from part A is wrong, if you use it and you plug in correctly 33, you're going to get 1 point. You're not going to get 2 points, but you are going to get 1 point. All right? So guys, that's just like a tip for IB or for life in general. Just give it your best shot, dude. You're still going to get points. Okay? You're still going to learn. You're still going to blah, 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 blah. Okay? So yeah, just keep it in mind the day of the test, all right? There might be something really hard, or you might have no idea how to do A or B, but you look at C and say, okay, that has nothing to do with math. It has to do with cars. And you're going to, part C, you're going to put snow and you're going to get 1 point. I'm not even kidding. I'm not even kidding. Like, you could not answer A, you could not answer B, and you answer C by putting snow, you get 1 point. All right? So guys, get points wherever you can, right? Sometimes you can't do A, sometimes you can't do B, but you can do C, all right? Sometimes you can't do A, but you can do B and C. All right, that's fine. Just get points wherever you can. All right, don't give up. Give it your best shot. Come on. For part B, use the equation from part A. Blah blah blah. Estimate the speed at which the car was traveling before the brakes were applied. So that means D, because it traveled 33 meters, D is gonna be 33. Oops, 33. My K is still my K. And I need to find velocity squared. See? So, because I need to get velocity squared alone, first things first, it's being multiplied by something, so I'm going to divide by that something. So divide by that something, bada bing, bada boom, goes away with this. I end up with v squared equals whatever that is. So it's 33 divided by 0.00492. See? Cierto. So velocity squared is going to equal to 6707, blah, 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 0.317073. All right, this is supposed to be a point. Apologies about that. Just very used to putting comma there. Whatever. See? So to keep getting v alone, because it's squared, what's the opposite of squared? Square root. So this goes away with this. Square root of that whole thing. Velocity is going to be equal to that. So, bada bim, bada boom. Velocity is 81.8982. All right. If you want to do significant figures, you count 1, 2, 3. Look at this 8. Do you round it up or down? You round it up because you have a 9 right next to it. It's 5 or above. So with significant figures, you put 81.9. All right. Don't forget your units. Kilometers per hour. Okay. So that is for part B. All right. And now for part C, we already talked about it a little bit, but after the brakes have been fully applied, one other variable besides speed that could affect stopping distance. Guys, this isn't even like math, it's just like context, see? So stuff you can say is whatever. I'm just gonna show you the answer key, okay? I think it's gonna make more sense if I just show you it like that. As you can see here, there's some of the stuff we talked about. So here you have a puzzle answer. We said weather conditions. That's when we said snow. That's also when we said mud. Conditions are types of brake, weight or type of the vehicle, road material. Here's the wind we talked about. Here's the friction we talked about. Traction, the gradient, if the thing has like a slope, right? It's going to be different than if it's flat. All right, guys, there's a million different things. You just got to land one of them and you get your point, see? The only thing you can't do is fuck up in the sense that you say, the time of the brakes can be slow reaction time or an inexperienced driver. Okay, and the reason we say that is because that has to do with the driver. It doesn't have to do with the car. See, but yeah, I mean that's whatever. I mean you can write down lots of these, and I'm sure you're gonna get the answer that you need. Okay, but yeah, the things down here, some of you might be thinking like, but that does affect stopping distance because if you're an inexperienced driver, then you're going to have a slow reaction time and the stopping distance is longer. Okay, you're right, but technically that has more to do with like the reacting, like the stopping distance considering reaction, okay? Or stopping distance considering the experience of the driver and stuff like that. In this case, as you can see, it's a bunch of sort of like external stuff. See, so completely external. This one is more like internal. It has to do with the drivers, okay? So again, I know that part's like a little shitty, but this is the weirdest exercise just because it's not very clear. Like part A is tricky, part C has some specifications, but once you get off, once you find the K, everything else just kind of flows. See? So again, I think this exercise and this test it's hard, dude. It's hard, and I don't think it's very straight. It's hard because it's not straightforward. See? Usually there's a very clear method to apply. In this case, the method is you just have to assume a bunch of stuff. See? I don't like number 6, but I tried to explain it the most intuitive way possible. I hope it helped. And yeah, see you around. Good luck. Alright, so now for number 7, we have that a rectangular box with an open top is to be constructed from a piece of cardboard that measures 48 centimeters by 30 centimeters. So our units are centimeters. Alright, cool. Squares of equal size will be cut from the corners of the cardboard as indicated by the shading in the diagram. So shading in the diagram, that means that this is getting cut off. This is getting cut off. This and this. See? And the side of each is x. See? Remember that these are squares. So this is a square, this is a square, this is a square, this is a square. See? All of the sides are x. So that's going to be useful down the line. I'm just pointing it out so that we understand what's going on. So the volume of the box in cubic centimeters can be modeled by the function blah, where 0 is less than x is less than k, where x is the length of the sides of the squares removed in centimeters, as I said before. See? All right, and for part A, we need to find the maximum possible value of k in this context. So before anything, some of you are probably a little confused with why this says cubic centimeters, okay? Now, what I need you to understand is that cubic is related to volume. So whenever you have a distance, okay, that's going to be units to the power of 1. So that's like thinking of centimeters to the power of 1, okay? When you have an area, okay, an area is going to be units squared. So that would be like centimeters squared. And whenever you have volume, okay, which is like a 3D shape, whatever, okay, that's units to the power of 3. And this is when you call it cubic. Okay, when it's to the power of 3, it's cubic. When it's to the power of 2, it's squared. When it's to the power of 1, it's distance. When it's squared, it's area. When it's cubed, it's volume, okay? Which should be centimeters to the power of 3. All right, so that's just a little bit of a context in case the word cubic scares you. Now, maybe it scares you a little less. So for part A, we need to write down the maximum possible value of k in this context. Now, a lot of times people freak out with these kind of exercises. They don't know where to start, and what I push you guys to do is to really try to explore the intuition of the problem, okay? Why would there be a maximum value for x? Because what k is doing is that it's limiting x with how big it can be. So why should there be a limit to x? In fact, what is x? X is the length of the side of the squares removed in centimeters. So if x has a limit, being k, if x cannot be bigger than k, then there's a certain moment in my process where I cannot remove like more squares of the cardboard. Alright, I know some of you might be thinking like, okay, where the hell are you going with this? The idea is the following. So let's make x a little bit bigger. See, let's imagine that x is just, I don't know, 2 centimeters bigger, okay? So now we're calling this x, alright? If this is x now, that means x also goes all the way over here. This is still legal, right? It's still legal because on every one of my squares, it's now a little bit bigger, see? And actually, now that I think about it, because it's a square, it would actually look like this, see? So if I make x bigger in that way, now the squares that I'm removing are this, see? Now, if I keep making x bigger, eventually you're going to notice that I'm going to run out of space. See, what if I make it this big? Well, now I have no more cardboard to cut out, see? And the problem happens because if I make it bigger than this orange square, for example, if I make it this green square here, now suddenly, if I cut this out, okay, if I'm calling that x, then that means that if I call this x, just give me a moment, if I call this x this big, okay, so that means x would go all the way here, x would go all the way here. If I make it this big, then on the other side, I can't cut it on the same like amount, you see? In fact, if I cut it once on the light green, on the dark green, I have all this space that I'm missing. So basically, there is a sort of gap of how big I can cut one of my squares, see? And how can I identify how big that number should be? Well, look at your sides, see? So it's a rectangle, right? And up top, I have the side of 48. And on this length over here, I have the side of 30. And so my limit is definitely going to be near the 30. And so the maximum squares that I can cut out are some that cut down right down the line like this. See? And an x value that cuts down the line like that, all right, means that this 30 is actually getting split into 2. 30 divided by 2 gives me 15. For part A, k equals 15. X cannot be bigger than 15, or else this 30 just doesn't have enough. See? The moment it's equal to 16, you're not leaving enough space for the other cutout. Okay? So again, intuitively, think about the context of the problem. Okay? X has a limit because you can't, you know, cut cardboard where there isn't. See? And if your X is big enough, you run out of cardboard to cut out. Where's the limit? You look at the smaller side, which in this case is 30, divided by 2 because you're cutting it in 2. So yeah, k equals 15. That is for part A. For part B, we need to find the value of x that maximizes the volume of the box. So, keyword, maximize. Okay, whenever you see the word maximize, you should be thinking of optimization. So whenever you are optimizing, all right, you have a couple of tools, but the main one is going to be derivative. Okay, whenever you do the derivative of something, it helps you optimize it. All right, so if I take v of x and I write down the formula, which is 48 minus 2x, 30 minus 2x times x. If I find the derivative of this, I can, get somewhere, okay? I can find how to optimize it, etc. I'll explain in a moment why it works that way, but for now, I really need to keep in your mind, if you want to optimize, you get the derivative, period, okay? And when you optimize, there are two things that can happen. You either find the maximum, or you either find the minimum. That is it. All right, so that being said, because my plan is to do the derivative, ¿cierto? Let's see if I should do the derivative now or I should move some numbers around. If I do the derivative now, it's possible, but you're going to encounter this thing called derivative of a multiplication. There's like a chain rule going on. You have 3 parentheses. It's a little bit annoying. So what we're going to do is actually develop this exercise a little bit and then do the derivative, okay? There is no rush to do the derivative. Sometimes you want to leave it a little more pretty so that it's easier to work with. So right now, I'm going to do some distribution here. So I'm going to do 48 times 30, which gives me 1,440. Over here, I have 48 times negative 2. So that's going to give me minus 96x. Then I have negative 2 times 30. It gives me negative 60x. And then I have positive 4x squared. All of this still being multiplied by this x hidden at the end. So I'm going to go ahead and put parentheses here. All of this times x. Let me combine like terms, and we can see that I end up with 4x squared, so that's this guy here, minus 156x, so that's these two guys, plus 1,440. All of this being multiplied by x. So that means I end up with v of x equals 4x cubed minus 156x squared plus 1,440x. All right, cool. So the value of x that maximizes the volume of the box, we now need to find the derivative. And so if I do the derivative of this, I am working with what we call the derivative of the exponents. And now let me pull out your formula booklet so that you guys know exactly what I'm talking about. Here is our fancy formula booklet. Remember that the day of the test, you walk in with the formula booklet, the pen and pencil, the calculator, your big brain, and a lot of energy to do well. See? So get familiar with it. Eventually, in my formula booklet, you will find the derivative of an exponent. Here it is. See? derivative of xn. As you can see, well, this is a little bit harder to follow, so through an example it's a little bit easier, but basically, imagine you have x squared, see? What's going to happen is first, the 2 is going to go down in front multiplying. So notice how this n went down multiplying. So that means I'm going to have 2x. And up top, I have my exponent minus 1. So I'm going to have 2 minus 1. So exponent of x squared is 2x to the power of 1. Most people just leave it as 2x. Let's do one more example. Let's say I have 2x to the power of 3. So here, if I do the derivative, it would be 3 times 2x to the power of 3 minus 1. So that would be 6x squared. All right? So that is how you do the derivative of an exponent. All right? So over here, all I really have are derivatives of exponents. So if I do the derivative of this, I end up with 12x squared minus whatever that is times 2, 312x plus 1440. See? All right. And so when you do the derivative, the big step in order to optimize, okay, is that you equal this to 0. All right, and this right here, guys, is actually a very, very, very important step. And I really, really, really need you to understand why I just did it. Guys, imagine you have a function that looks like this. Okay, and this is your classic. Okay, you have a function that looks like this. Where is the... First of all, what the heck is this? This is what you call a parabola. Okay, the parabola usually looks like this or like that. Okay, and so when you do the derivative, okay, this now turns into slope. Okay, some of you might also know it as gradient. And so now when I equaled it to 0, I was actually equaling it to a slope of 0. I was not equaling it to x equals 0. No, I was equaling my equation to slope equals 0. Basically, on this step right here, I am asking my function, what is x when the slope is 0? What is x when the slope is 0? That is what I'm asking it, okay? And why would I ask that to this parabola here, for example? Why would I ever do that? The only reason you would ever do that is because, well, a slope of 0 looks like this. It's a horizontal line. Remember that a slope that is undefined, okay, is when it looks vertical, okay? The explanation of this is that the equation of a slope, which is over here, I think if you look for gradient, it shows up. See, the gradient formula, see? Look at the gradient formula. It has y's on top, x on the bottom. If it has y's on top, that means up top, it's like the change in vertical. And if it has x's on the bottom, it's the change in horizontal, okay? So what I'm saying is that if I have a slope of 0, that means my numerator is 0. So my change in vertical is 0, and I have some change in horizontal. If my change in vertical is 0, but I have a lot of change in horizontal, then I have something like this. A bunch of lines in a row where I have change in horizontal, but no change in vertical. You put all these dots infinitely next to each other, and boom, you end up with a line. Okay? That is what's going on, and that is why. Okay? That is why slope of 0 gives horizontal. That is why slope undefined gives vertical. So, what the hell? I come back to this parabola. Look at the slope. Okay, look at the slope. The slope here is like, on this point, yeah? The slope here is like, I don't know, 1. The slope here is like 1/2. See? Well, what is the slope on the maximum? The slope on the maximum, ladies and gentlemen, is... Okay, that was a horrible line, but on the maximum, it's a slope of 0. Okay, and that is something very important that you need to keep in mind. When slope is equal to 0, equal to where's my equal sign? When the slope is equal to 0, we have a maximum, okay? And this parabola is an excellent example of that, see? That is why I equal to 0 up here, because I'm trying to find a maximum, okay? Something else you guys need to keep in mind is that my equation can look like many different things, okay? I could have an equation that looks something like that, okay? Here, if I equal it to 0, I'm going to find 3 points. This one, and this one, okay? I would have 3 maximums, all right? In this case, I'm probably going to end up with just one, or 1 or 2, but we'll see what happens, okay? So that's a little bit of context of what happens and why we equal it to 0 and all that good shit, see? So if I equal to 0 from this context, how can I find the value of x? See, how can I find the value of x? I already asked it for the slope of 0. I already know I'm going to get a maximum or maximums. But how do I find the value of x here? So notice, guys, this, get familiar with it. See, you have an x squared up here. See, you have x to the power of 1 over here, and technically you have x to the power of 0. See, so what is this? This is a parabola. Okay, let's remember that the original function of this is ax squared plus bx plus c. Okay, that is for parabolas. And so your tools for parabolas are usually 3. You either use factoring, you either use the quadratic equation, or you straight up just use your calculator. Okay, calculator, you like graph and stuff like that. See, there's a couple ways to do this. What I'm going to choose to do is, what will I choose to do? Give me a second. What will I choose to do? Can I divide this by 12? Yes, I can. I'll use the quadratic equation, all right? But there's a lot of options. Pick whatever works for you. I'm just going to show the quadratic version okay? The quadratic equation looks like this. You have x equals negative b plus or minus square root of b squared minus 4ac divided by 2a. And so this is actually used for finding the zeros, okay? Which is exactly what we need to do because I am equaling it to 0. Basically, it's going to give me the values of x that work, see? Now, what is a, what is b, what is c? Look at this. This is a next to x squared, so a is 12. This is b next to x to the power of 1, so b is 312. Negative, very important, negative. And c, following the logic, is 1,440, see? So again, this looks a little bit nasty, but have a little bit of patience. We're going to have negative b, so that's 312, plus or minus square root of negative 312 squared, minus 4 times 12, times 1,440, divided by 2 times 12. So using my calculator a little bit, let's see what happens. 312 stays outside. Let's see what happens inside. So inside we're going to have 312 squared, right? Minus 4 times 12 times 1,440. So that gives me this, which is probably wrong because it's negative. So that means what I did wrong was over here, good thing I noticed, I needed to put negative 312 and the squared right outside. See? So my bad there, guys, but hey, happens to anyone. Good thing I saw it. So with that small detail, I end up with a positive value. I get the square root of this. It gives me 168. So I end up with the square root of 28,224 divided by 2 times 12, 24. So that means I have 312 plus or minus what I found here, 168 divided by 24. And so now I apply the plus or minus. See? Basically, I'm going to get 2 values of x. I see which makes more sense. And so with 2 values of x, see, on the plus version, we're going to have 312 plus 168 divided by 24. So let's see what that is. 312 plus 168 divided by 24. gives you 20. The other version, which is negative, we have 312 minus 168 divided by 24, which gives you, let's see, so it's almost the same thing, just that over here it's minus, divided by 24, 6. So I have 6 and 20. Now, most of the time, out of context, you pick the one that makes more sense. See? So guys, which one makes more sense? 20 or 6? Most of the time, one of these is positive, the other one is negative, and it's like, duh, don't pick the negative one because you can't have negative sides. But, ladies and gentlemen, there is something else that gives me a hint here. Remember part A, we said the maximum possible value of k in this context is 15. Why is it 15? Because if it's more than 15, you run out of cardboard to cut out on the other end. See? So, once again, and this is a big tip for math IB in general, usually for part B, you need what you used in part A. Okay, not always, but sometimes it's like, sometimes it's a very big hint. Okay, so between these two, you actually pick 6. You cannot pick 20 because we found that the maximum of k is 15. Okay, if you picked 20, that means one of your cardboard cutouts goes like this, and then when you try to cut out over here, you don't have enough cardboard to cut. It's that simple. Okay, all right, so fuck it. You pick 6 because it's below 20, literally. Okay, don't forget your units. For part B, we answer that x has to be 6 centimeters. And now it gets a little bit exciting. Worth for 3 points. Da-da-da, we have that a second piece of 48 centimeters by 30 centimeters cardboard is damaged, and the strip 2 centimeters wide must be removed from all 4 sides. God dang it. A box will then be constructed in a similar manner from the remaining cardboard. And so now we need to calculate the maximum possible volume of the box made from the second piece of cardboard. So this second piece of cardboard, okay, is like the original one, but a little bit smaller. And so the hard part here is really trying to understand how smaller it has to be. So notice how it says a strip of 2 centimeters wide. See? So and this is the hard part, okay? Because really understanding what it's saying is probably the biggest challenge here, okay? And so in the original scenario, we had 30 and 48. And then we said we're going to cut out x on each of the sides and work from there to fold it and shit. See? Okay. What's happening now, ladies and gentlemen, is that we have the same 48 and 30, but before cutting out the x's, see, before putting in the greens, it gets damaged. See, someone dropped it, it got wet. I don't fucking know. See, someone fucked up. Someone fucked up hard. And we need to get rid of a strip of 2 centimeters wide from all 4 sides. And so the keyword here is strip, okay? So if it's a strip, it's like a long sort of thing, okay? So that means they get rid of 2 centimeters here, 2 centimeters here, 2 centimeters here, and 2 centimeters here. That's what happens. So now you are getting rid of, well, 2 centimeters from this 30, 2 centimeters from this 30. That means that your new rectangle is going to be a little bit smaller, okay? And you're going to have, well, 30 minus 4, I mean 30 minus 2 minus 2, just so that we understand. So it's this one and this one, gives you that 26. So your new rectangle is now 26 on that side, on the vertical, and on the horizontal, well, it's the same idea. We're getting rid of this 2 and this 2 out of the 48. So that means I'm going to have 48 minus 2 minus 2. 44. Compound. And now, and only now, we cut out some amount of x. Alright? So that is what's going on, guys. Okay? That is the context of the problem. That is what's happening. Okay? And now notice, you need to find the maximum value of x from here. Okay? And I know some of you might be thinking, what the actual fuck? How do you expect me to get it from here? And what I'm going to tell you is, yo, chill the fuck out. Remember, we have the volume of the box, see? And it's over here. Now notice, the volume of this box, where did this 48 come from? This 48 comes from here. Where did this 30 come from? This 30 comes from there. Where does the 2x comes from? That 2x comes from this x here and this x here. Where does this other 2x comes from? It comes from this x here and this x here, affecting the 30s. See? And this last one, I'm not really sure, okay? But probably has to do with the fact that it's volume, so you need to multiply it so that you end up with something cubed, okay? But fuck it, the intuition is the same, all right? You're gonna make a new equation following the parameters down here, see? And so following the same logic that's there, see, let's remember that the original one, first I'm gonna put the original, okay? So if the original one was 48 minus 2x, right? 30 minus 2x, parentheses x, that means the new one with the new sides that I'm picking here, okay, it's gonna have to be, well, the new v of x is 44 minus 2x, 26 minus 2x times x. And so now we need to find the maximum of this. Right, and with that, you're good to solve everything that's coming your way, okay? So the rest of the video is really, or this part of the video, depending if you're seeing the video of the whole test or just one by one. What's coming next is the same process as part B, just that with different values. See, if originally we started with this and try to maximize it, we start with this and try to maximize it. Now we're starting with this and trying to maximize it. See, but the process is the same. You're gonna see that again. I'm gonna choose the quadratic equation, and my A's and B's and C's are gonna change, but the concept, the intuition is the same. You're still going for slope of 0. It's the same fucking process. Okay, the hardest part is understanding that you end up with these sides, 44 and 26, and that then you find how much x you get rid of. Okay, again, this is a very much of a language thing. Really gotta reread it a couple times until it enters your brain. See? And I think it's a little bit shitty, but it happens, that if you don't know that the word strip makes a reference to something long like this, it's a little bit hard to follow. See? Some people might assume that they're getting rid of another square. Nah, dude, you're getting rid of a strip. Okay, you're getting rid of a whole sort of like long section. Okay? So anyways, let's keep going. See? So now with the new one, I need to find the derivative of that. See? So let me make a little bit of space. Let me erase here so that I have more working area. But as I said, the process is the same. So because I need to maximize, I need to find the derivative. And so let's make this a little bit more nice to look at. See? So first of all, 44 times 26. Okay, so I end up with v of x equals 1,144. 44 times negative 2x gives me negative 88x. And negative 2x times 26 is going to give me negative, brain fart, I think it's 52. It is 52, 52x. And negative 4x squared. See? all of this being multiplied by x. So we'll see how that rolls out. So I end up with negative. Oh, this is not negative 4x squared. This is positive 4x squared. My bad. My bad. I missed that. Negative times negative. So I end up with 4x squared minus whatever that is. So 88 plus 52. All right, cool. So 140, 140x plus 1144. All of this times x. And so I end up with 4x cubed minus 140x squared plus 1144x. So now I find the derivative. See, I find the derivative of this guy here. Again, derivative of an exponent. So 3 times 4 gives me 12. Exponent 3 minus 1, 2. 140 times 2, 280. The exponent minus 1. And here it's just 1 times all of this. So it stays like this. Oops. 1,000. Oops. Plus 1,144. Now I equal it to 0. See? And for you guys that are sticking around and that are learning a thing or two, why did I equal it to 0? What was intuition? Aha. This is slope. I am asking, what is x when the slope is 0? Why would I do that? Because when the slope is 0, we have a maximum, okay? Maximum or minimum, okay? This is something I failed to mention earlier. You have a maximum or a minimum, all right? You use it for optimizing. So, how can I solve this from here? I suggest using the quadratic formula. So A is going to be 12, B is going to be negative 280, C is going to be 1,144. So I plug this in into the quadratic formula. The rest I'm plugging it into this one, okay? Just so you guys don't get lost. I'm going to have negative B. It's just going to be positive 280. Let me use another color because there's a lot of shit going on. So positive 280 plus or minus square root of this b squared, so negative 280 squared, minus 4ac, so that's going to be 4 times 12 times 1,144. All of this divided by 2 times 12. So what does that give me? It gives me 280 plus or minus square root of whatever that is. So it's going to be negative 280. I put the squared outside, very important. Committed that mistake earlier. Live and learn just like anyone else. All right, 23,488, I think it was, 88 divided by 24. So what is the square root of that? It is just about, whatever the hell that is. See, so 153.2579. 2579. Let's put the whole thing. 5. Okay? Divided by 24. So, I'm going to go into directions. See? I'm going to choose the positive side and the negative side. So the positive side, I'm going to do it first. So if it's positive, see, I'm going to have 280 plus around 153, comma, let's just leave it at 26, okay? Comma 26 divided by 24. Sure. So that's going to give me, well, 280 plus 153.26 divided by 24. That's going to give me 18. 18,05. Sure, I don't care. For the negative version, we're going to have 280 minus 153,26 divided by 24. And that's going to give me kapow divided by 24. Bada bing, bada boom. 5.280. 281. Sure, I don't care. Whatever. So, now I need to see. So, both of these give me like a maximum volume. right? But I need to see which one I gotta use because, I mean, it's two different maximums. One of them is legal, the other one's not. How can I tell which one's legal? So, using the same logic as before, where this 30, I cut it in two and said, okay, how big can the squares be, right? And I ended up with k equals 15. Well, I follow the same logic. This 26 divided by 2 gives me 13. Okay, so the the value of x cannot be bigger than 13. As we see down here, whoops. Yep, as we see here, I have 18 and 5,28. Is one of these bigger than 13? Yes, this one is bigger than 13, so I do not consider it. The value of x that I use is over here. And so because I use that value of x, I go ahead and plug it again into my volume formula. See? Actually, it's the same volume formula as the one I got in green. See? Whatever, you can use any one you want. See? Point is, your value of x is going to be 5,281. So, plugging in a value of x of 5.281, we can see over here that I'm going to have 44 minus 2 times 5.281, close, close, 26 minus 2 times x, x is 5.281, close, close, parentheses again, 5.281. This gives me, and this is the answer for part C. For part C, I'm going to have that the volume, see, has to be 2,726 points. If you round it up with that 5, cierto? Actually not, just leave it as 13, whatever. 13 centimeters, because it's volume cubed. That is the answer for number C, and that is the whole exercise. Hope it helped. All right, and now for number 8, we have this thing that talks about password entropy. They tell us that password entropy is a measure of the predictability of a computer password. The higher the entropy, the more difficult it is to guess the password. And so the relationship between the password entropy P, measured in bits, okay, so this is important, we have one variable P, and the number of guesses G, so G is number of guesses G, well P, they tell us, is password entropy. Required to decode the password is given by blah, so this whole equation is what we have to work with. Alright, I know it looks nasty, okay? But for now, you can think about it like one of these is x, the other one is y, you have a log going around. The 0.301 is just a constant, it's just a number. Let's not be too scared right now, okay? There's no reason to be scared. Part 8. Calculate the value of P for a password that takes 5,000 guesses to code. Alright, we still don't need to get scared. It's fairly straightforward. Number 8, part A, as we can see, what we have is calculate the value of P for blah, 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 blah. Okay, so all I know is that I have this equation here. See, 0.301P equals log 10 G. Alright, so it's very important, you guys, that we walk around with a good intuition about these exercises. Okay, so when they tell you to calculate the value of P, that means that P remains as what? It remains as a variable. So P is something that is not going to change. And then they tell me 5,000 guesses to decode. So guesses is which variable, P or G? Well, I know that P stays as a variable, so I'm not going to touch it. I know that G is number of guesses. That's why it's important to highlight buzzwords, as I put in yellow. And so now G is going to equal 5,000, given what they tell me here. And I need to find the value of P through that. Okay, so I'm going to put 5,000 over here, and we see what happens. Okay, now from here, I'm sure a lot of you, give me a second to open this up. It's probably going to be important in a second. Yeah. So from here, a lot of you are probably like, yo, what the hell, what do I do? See? Now, first things first, you guys. You need to get P alone. See? There's only one variable here. You need to get the guy in red alone. Okay? Right now, the guy in red, how is it being affected? It has a 0.301 right next to it being multiplied. That means you need to, what's the opposite of multiplying? Dividing. So you multiply by 0.301. This goes away with this. And I end up with some number on the right side. So I end up with P equals log base 10 parentheses 5,000 divided by 0.301. Now, guys, I know a lot of you from here are like, dude, what the heck is log? When I try to put it into my calculator, like the little 10 doesn't appear. Like, what do I do? All right, guys, this is why it's important to know some certain stuff about intuition, the intuition of logs, and stuff like that. See? First things first, logs have two components. Okay, even in this exercise, you can see it. You have what they call the base. Okay, so this can be base 10, it can be base x, it can be base 2, it can be base 5, and a whole different thing is what goes inside the parentheses. Okay, so just bear in mind that this base, okay, can go changing and it affects how the log behaves. Now the default, okay, como lo que viene por de fábrica, como the default, all right, is always going to be 10 for log. Okay, so for log, the default is 10, and for natural log, the base is e. Okay, that's just your defaults. Okay, so when in your calculator, for example, you write log 5, it is assumed, because it is the default for log, that there's a hidden 10 here. Okay, it's not so different that when you find the square root of 4 and you equal it to 2, it's because by default there's a hidden 2 here. Okay, so you're asking the calculator what number multiplied by itself twice gives you 2. Okay, it's very different when you have something like this. It's which number multiplied by itself 3 times gives you 2. And the default is that this number here is hidden because it's assumed it's 2. If they change it, then it shows. Okay, in this case, it's a little bit tricky because they put the 10 even though the 10 is the default. So technically, over here for this exercise, I can just put a fraction using alpha f1. Okay, alpha f1, then the first option. Blah blah blah. I can do log 5,000 because the 10 is implied, and I divide it by 0.301. Okay, and that would be quite literally for part A. See? Now, I know some of you might be thinking, okay, but what if the day of the test, instead of log 10, they put, log 11? Come on, fuck, like now I can't do anything. All right, guys, the day of the test, you walk in with a couple of things, okay? With your calculator, with your formula booklet, with your brain, with a pen and pencil, hopefully don't forget it, and like 30 minutes of sleep, okay? And everything you've learned the past 2 years of this thing they call AB. See? Get very familiar with all the tools you're going to use that day, because those are the tools you're going to have to play with, okay? And one of them is the graphing calculator. And the cool thing about the graphing calculator is that you can literally do fucking anything, okay? You can, dude, it's crazy, okay? You can do whole summations. You can do whole integrals if you don't like integrals. You can do whole derivatives as well. And lo and behold, if you go to math, see, now I have to find it, but I know it's around here. Here, log base, see? So if you press math, okay, and this is the thing, I didn't know exactly where it was, but I knew it was in here, okay, and that's the level you guys need to reach, okay? Maybe you don't know exactly where to find it, but you know where to search, right? You don't know where your hammer is, but you know which room it's in. Okay, that's what matters. Okay, so for this exercise, even if you don't know that 10 is the default base, you can put it in fraction, you can press math, you can scroll all the way down, you can press log base because it lets you put the base. So you put 10, put parentheses 5,000, and then below you put 0.301. Press enter, you get the same answer, but now you're a little bit more relaxed, okay? So whenever you need a plug-in base, if it's 10, if it's different than 10, it doesn't matter. You have the tools to do it, okay? That's the main message I wanted to show, see? So again, I know some of my videos, they extend a little bit longer than maybe they should, but I think it's important that you guys know these things. So whatever, man. You picked this video for a reason. Fuck you. Part A, 8A is going to be, as we see in this calculator, 12.2889. If you want to leave it in significant figures, what you do is that you count 1, 2, 3. The third one to the right, should you round it up or down? You do round it up because it is 5 or above, in this case 8. So the significant figures following the mark scheme, actually, it's going to be 12.3. 12.3 what? Don't forget your units, bits. All right, so that is part A. We talked a lot about logs, but it's going to be helpful down the road. For part 8b, okay, let me make a little bit of space. Kapow. Yeah. For part 8b, we have write down g as a function of p. Now, a lot of people here are like, what is this saying? See? So when they tell you write down g as a function of p, it's basically like, get me an equation where I can express g in terms of p. You know when they talk about in terms of? Okay, this is the same. Maybe that's a little bit more friendly. I mean, this is the same as if they told you, write down g in terms of p. It's the same thing. It's literally the same thing. And so what you need to do is that you need to take this equation that we have in blue, okay? Well, that I just put an asterisk in red. So this equation, yeah? And you have to reach g equals something, 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 p, okay? So you need to have g alone, okay? That's the key idea. You need to keep g alone. G is alone, and whatever else on the other side is going to be something, 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 p, okay? We're about to find out how to do that, okay? Now, for parts 8b, it's a little bit tricky because my equation is 0.301p equals log base 10, and the number that's inside is g. So here, it's a little bit harder because what a lot of people might want to do is just, oh, you can divide by log base 10. No, that's not really how it works. I'm sure there's a way to do it that way, but I think there's a simpler way, okay? So right now, you need to get g alone, and you're in a tough spot, right? G is like inside the log, so it's hard to work with that. What do? Well, know your tools. Know your formula booklet. Find everything you can in your formula booklet about logs and see if it helps. Especially when you're stuck, this is a good thing to do. So you're stuck here. You don't know what the hell to do. You don't know what the fuck to do. G is in here. There's a log next to it. You never understood logs. It's the day of the test. God damn it, what do I do? Pull out your formula booklet. Look for everything you can find about logs. Where might logs be in these chapters? Number and algebra, something I never understood. Let's go to that page. Page 3 or 4, it's probably around there. Page 3 or 4, lo and behold, exponents and logarithms. There it is, okay? There it is. And so what this is telling you is that this is actually like a log property, which is, I don't know what's the name of it, but I like to think about it like the definition of log. Definition of log, see? The thing about log is that it's a cool way to connect exactly exponents with logarithms. See, so notice how you can go from a to the power of x equals b to x equals log base a times b. See, these are the same a's, the same x's, the same b's, the same a's, the same x's, the same b's. See, and there's a couple rules that go behind it, but it's pretty general stuff. Okay. Point is, you can turn this log into this other sort of equation thing. See? So let me just go ahead and write that on this side because it's gonna be damn useful. Let's put it in purple because why not? So we have that a to the power of x equals b is quite literally the same as x equals, yeah, log base a times b. See? I mean, not whatever. See, parentheses b. So if I try to apply this, and I need to go like piece by piece, let's go piece by piece then. So in this context, what is A, what is B, and what is X? So in this context, following this here, okay? In this context, A would have to be 10. Why? Because we're talking about log 10, ¿cierto? I mean, the base 10, okay? So A is 10, that means this A over here is also 10, okay? Okay. What else? What else? What else? So B is what's inside the parentheses, which is just G. All right, cool. So we have We have this. That means we have this. I'm only missing x now, of course. What is x? X is what it equals to, what the log equals to. So x is it 0.301 or is it p? Newsflash, it's both. Damn. Yo, that's kind of cool though. So that means I got this, and I also got this. See, so if I go ahead and plug everything in so that I end up with what's on the left, okay? If I go ahead and plug it in, what I'm gonna end up with is, well, we said that A was 10. We said that X was 0.301p. And we said that B, the one that's alone, equals G. Ah, okay. So, damn, I'm just gonna rewrite it down here because I like it when it's on the left, because I'm like that. But look at that. I got G alone. And what were we trying to do? Get G alone. See? So I'm going to have G equals something something P. Well, in this case, P is on the exponent, but yo, I have something something P. I have G alone. That's all I need to do to write down G as a function of P. That is part B. Kapow! Look at that. All right. And now for part C, you need to find the number of guesses required to decode a password that has an entropy of 28 bits. Write your answer in the form blah, 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 blah. All right, so when they tell you this is what they call scientific notation, okay? And just so that we're a little bit friendly with this Z symbol is for integer, okay? What are integers, you guys? Integers are negative and positive whole numbers, okay? When I talk about whole numbers, an integer would be like -2, 1, 0, 1, 2, to infinity, okay? And also to negative infinity. See, let's not forget about, let's be inclusive, see? So, that is for integers, okay? So all it's really saying is that, yo, like rewrite your answer, just that you multiply it by 10, and this 10 is to the power of something, and that something has to be a whole number, okay? Oh, and A has to be between 1 and 10. So this is scientific notation. So if you guys want to Google it a little bit, or search for my other videos that have it, scientific notation is your buzzwords to understand this better. I'm still going to explain it now because some of you probably have never seen it and you deserve to understand it well immediately. So, for part C, find the number of guesses. Okay, so when they say find the number of guesses, which variable is that? Okay, by now you should notice you're trying to find G. Okay, so G is now going to be your variable. And what you're going to be plugging in is that it has an entropy of 28. See? And so the entropy of 28, they talked about password entropy before. So in other words, you can associate entropy to P. So that means that P equals 28. ¿Cierto? Cierto. All right, team. So that means for part 8C, I can take the fancy, formula that I put on the right side, and I can leave G as it is, and we're applying that P equals 28. See? That is a P. Why? Because that's what you said over here. Yeah. So G equals 0.301 times 28. All right, so you can go piece by piece here. See, for example, you can say, okay, 301 times 28. Okay, that's not like a whole number or whatever, so you end up with something a little bit weird. You end up with 10 to the power of 8.428. See? Now, is this what they're looking for? No, because as you can see, k has to be an integer. In this case, it's not. Okay, so some of you might try like combining the exponent. It's still not an integer, so there's still work to do. Okay. For scientific notation, what I suggest is get your answer like as raw as possible. Like get to the answer, okay, like the long string of numbers, and then convert it to scientific notation. And I'm about to show you how. So let's take that 10 and put it to the power of 8.428. So here's my nasty answer. See, my nasty answer is 26,791. 26,791,683. 2, comma 5. And so that means I have 1,000. Yeah. Wait, these are commas. Sorry. Kind of used to doing it in the other version. Yeah. So this is my number. It's a nasty number. It's super long, but you probably don't know what the fuck to do with it. See? So when you use scientific notation, it's basically like a nice way for this number to look prettier. Okay, and it's a way to sort of like define it better or whatever. See? Um, strictly speaking, what you want to do, so notice how they tell you that A is between 1 and 10. See? So basically, A can be whatever number it can be, but not above 10. So for example, if you want to start, okay, your scientific notation from here, and then writing everything else, you would be starting from 26. Okay, that's not legal. But what you can do is start it from here. Okay, so if you start it from here, what you would be doing, if I do a scientific notation, I would be putting 2.67916832. Okay, so that means basically I took this number from before, I took the first digit to keep it between 1 and 10, and I put everything else as a decimal, right? And I multiply it by 10 to the power of 8. Why does it work that way? Why do we multiply to the power of 8? Because, ladies and gentlemen, the cool thing about scientific notation is that it helps you move the thing I put in a very dark color, this guy, see? And so that is my decimal place, okay? So this is 0.5, ¿vale? Como 1.5, okay, that's the point I'm talking about, 0.5. And so the scientific notation, what it does is that it moves that decimal around, okay? Right now, my decimal is all the way over here, ¿cierto? It's like technically it's here, see? Technically it's here, and the way to move it back, okay? For example, take this long number, see? Just the decimal form or whatever, just so you guys understand the idea. So if I take 2.679, 16832, okay, and I multiply it by 10, what's gonna happen to the decimal? It moves one over. What if I multiply by 10 again? It moves one over again. Okay, so what if I multiply by 10 squared? How many times is it gonna move? Kapow! It moves twice. Yo, so that's what it's doing. So how did you reach 8? Well, I literally counted. 1, 2, 3, 4, 5, 6, 7, 8. And ladies and gentlemen, kaboom, you now understand scientific notation. So that is the answer for part C. If you want to get fancy, what you can do, which is, it's in the mark scheme, it also works, okay? You can say, okay, well, I need to put 2 point something, right? But I don't want to put the long string of numbers because it doesn't look nice. What you could do technically is say, well, this same number here, but you're going to be counting 3 decimal places for significant figures, right? 3 significant figures. This one, do you round it up or down? You round it up. So technically, this, you could leave it as 2.68 times 10 to the power of 8, okay? They're both in the mark scheme. They both work. That's it. Okay, whatever. That Anyways, that was a long explanation, but I'm sure someone out there needed it. So whoever it was, good luck, brother. You got this. Or sister. Yeah. Then they tell us that there is a point on the graph of the function g of p with coordinates 0, 1. Okay. Explain what these coordinate values mean in the context of computer passwords. I'm going to say one thing right away. Guys, if you reach this exercise and you have no fucking idea how to do part A, if you have no fucking idea how to do part B, if you have no fucking idea how to do part C, you can still do part D, okay? I know that usually you need to solve these exercises like, oh, part B needs part A and part C needs part B. So like if you get stuck at the beginning, you're stuck forever. Okay, that's sort of true. Okay, sort of true. Generally true, okay? But sometimes some of these exercises, okay, you don't need the parts from before. You can answer part D without anything else, okay? And I just want you guys to notice that, because the day of the test, if you're fighting for points, if you have time but there's an exercise that you're stuck on part A and you can't solve it, you tried all your tools, it's not coming out, look at part B, look at part C. Not only can it be a hint for what you need to do for part A, but also maybe it's an exercise you can solve without needing the stuff that's before it. And that's a free point right there, dude. So, there's a point on the graph of the function g of p with coordinate 0, 1. What does this mean in the context of computer passwords? So, we have 0, 1, right? And we have the function g of p, see? So 0, 1 means that you're plugging in 0 for p and getting that, technically, ¿cierto? This means that g equals 1, see? So, this is telling me, so let's remember that p is password entropy. So when entropy equals 0, then the password, okay? Sorry. When the entropy equals 0, then the guesses you need are 1. And if the guesses you need are 1, technically you know the answer, okay? So if you're a computer hacker, I guess this would be the case, I guess, I'm not sure, if your password is like 123. Okay, if your password is 123, the entropy is pretty much 0. It wouldn't take a lot of guesses. The computer would figure it out right away, okay? So the answer for this part, for part D, we're going to be saying that I would just express the point 0, 1 means that with an entropy of 0, the amount of guesses needed are just 1. All right, so that is what I would express. I'm sure that would get my score. If you want to know how the answer key has it, it's not anything from another planet. If a password has an entropy of 0, then the password can be guessed in 1 try, or the password is known. See? Again, notice how in this tab they tell you references must be made to both entropy and number of guesses. That's really like just use the buzzwords. Okay, when you use the buzzwords, you're going to be using entropy for P, guesses for G. Okay? But yeah, that is about it. That is for number 8. All right, and now for number 9, we have a classic. We have the cross-section of a scale model of a hill is modeled by the following graph. So technically this is a hill, maybe there's a tree on the top, who knows what the hell's going on, okay? Whatever, it's a hill. The heights of the model are measured at horizontal intervals and are given in the table. So they're telling us that for at x of 0, we have y of 0. So that means we have the point 0, 0 right here. At x of 10, we have a y of 3. So that means we have this point here is, you guessed it, 10, 3. And if we keep going, we have the same idea. This is 20, 8. Over here, we have 30, 9. And lastly, we have 40, 0. Okay, so that's the information the table is giving me. It might be useful or it might not. Let's see. Part A. Use the trapezoidal rule. Oh, shit. Use the trapezoidal rule with h equals 10 to find an approximation for the cross-sectional area of the model. All right, guys. So a lot of you probably read this. You read trapezoidal rule and you're like, damn, I don't know what the fuck that is. So let me give you a little bit of a 101. Okay, so the trapezoidal rule, the reason you use it is because it is, as it says here, an approximation for area. Okay, if you want to find the area of this hill, right, like all the earth underneath, if you want to think about it that way, if you want to find the area or what's in red, okay, finding the area of something with curves, like this here, of something with curves, can be very hard, okay? For example, if I say, okay, what's the area of, I don't know, like a rectangle? Well, you tell me what's the height, what's the length, you just height times length, you know, you're good to go, right? It's easy peasy when it's like straight edges, straight shapes, whatever, okay? In this case, you have a figure with a bunch of curves, and so what the trapezoidal rule does, and I think it's very important to understand intuition, what the trapezoidal rule does is that it takes each of these points that I just wrote down and makes a bunch of, you guessed it, trapezoids. Okay, so what you end up with are a bunch of figures that look a little bit like this. The trapezoidal rule says, okay, so I have a shape that is something like this. I have a shape that is something like this. I have a shape that is something like this, okay? And of course I missed one over here, probably looks like that. See? So if you find the area of number 1, number 2, number 3, number 4, you're going to end up with pretty much the area of the hill. The thing is, clearly there are some parts that I'm missing. For example, I'm missing this whole section here. I'm missing a little bit of this. You get the idea. When you use the trapezoidal rule, yes, you get very close, but you don't get the exact value. But it is very good for making approximations, and it isn't an integral, so it's a little bit more friendly, okay? So that is what the trapezoidal rule does. It finds an approximation, as I put here, of the area for whatever thing. In this case, blah, 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 cross-sectional area of the model. Okay, sure. It's just another way to say area, just very fancily. Just whatever, man. Fuck you. Trapezoidal rule helps you find the area under a figure at its approximate values because it draws a bunch of shapes. It finds the areas of the shapes. Now, if you're at the test and they tell you trapezoidal rule, well, first of all, freak out for 1 minute because trapezoidal rule is fucking weird. But then relax because you're gonna remember this video and you're gonna remember that some guy online told you, yo, the day of the test, you're going to walk in with a couple of things, okay? You're going to walk in with your calculator. You're going to walk in with, I don't know, pen and pencil. You're going to walk in with like 2 hours of sleep. You're going to walk in with a lot of motivation. Maybe a little bit of teenage depression. I'm not sure. Depends on each case to case. And you're going to walk in with your brain. Very important. You always have your brain. It's your, you know, it's your friend. It's your brain. And the formula booklet. Okay, guys, the day of the test, these are your tools. Okay, so get familiar with them, particularly the formula booklet. Okay, so within the formula booklet, you might not know the trapezoidal rule by heart, but you will know that the formula booklet has it. Okay, so you open up your formula booklet the day of the test, and you try to find trapezoidal rule. See, so you're probably just going to start looking through the pages. You're not going to care about the chapters, but eventually you're going to find doop-de-doo, da-da-da-da. There it is. See? Trapezoidal rule. Okay? Trapezoidal rule looks a little bit weird. Yes, I fully agree. But let's really try to understand what this formula is telling us. Okay? So, first things first, here you have this symbol there. See? This symbol there means an approximation. Okay? And so, much as I told you, it's like the integral that calculates the area perfectly. You can make an approximation using the trapezoidal rule. Okay, so the trapezoidal rule is actually this. This is the trapezoidal rule. Okay, and where is the part where you have like these shapes going on here or there? Let me explain. So you don't have to understand this formula by heart, but really just understand what's going on. So notice how you have a bunch of y's. Okay, y is related to what? Ah, it's your y-axis. And your y-axis, is it horizontal or vertical? Y is your vertical, x is your horizontal, okay? So you can think about your y values as like how tall something is, okay? So each of these y values is like the tallest point you can find, see? Notice how you have from y0 to y1, y2, until yn minus 1, and yn, okay? I know that's like, okay, what's going on? Basically, when they talk about y0, okay, it is your first value for y. And when they talk about, I'm actually going to write that down. This is important. So y0 is first value for y. That's why they call it y0. And yn is going to be your last value for y, okay? That means that y1 is, you guessed it, it's going to be, well, technically your second value, okay? Because your first is on y0, see? For y. And yn minus 1 is going to be your second to last penúltimo, ¿cierto? Second to last value for y, okay? Now, I know right now some of you are thinking like, dude, what the hell is going on? Just focus on the fact that you have a bunch of y's and this subindex, okay, whether it's 0, whether it's n, whether it's 1, 2, 3, is a signal for which y it should be, okay? So the most important ones to define right away are, of course, the first and the last, okay? So, looking at this graph here, which is my first y? This point here is technically x0, y0, see? So that means my y0 is, actually, let's make a little table here, why not? So my y0, following this, is 0, see? ¿Cierto? This guy with this guy, right? The second point is x1, y1. So my y1 is 3. My y2, well, I have x2, y2. It's the next point that they give me. How did I find these points? It's the table that they gave me here. Okay, it's arbitrary. You define it, but they're usually going to give you the points. Okay, x2, y2 is going to be 8. By now, you guys have probably got the idea. So that means that y3 is over here with equal to 9, and y4 is equal to 0. Okay, so y3 is equal to 9, and y4 is equal to 0. See? Now, some of you might be thinking, okay, so right now I have this guy, I have this guy, this guy. Technically I have this one because like second to last would be, well, this y3. But you might be or maybe you don't even have that figured out. Maybe this is still confusing. Which one is your last y? Because I don't see a yn here. I see y0, 1, 2, 3, 4. So which one is my yn? Guys, what is the intuition of this n? I told you, it is the last value for your y. And in this context, what is the last value for your y? It is 0. At what location, at what slot? At y4. So y4 is the same as yn, and I put yn in the context of it's my last, okay? So your last, or your yn for the formula is going to be 0. So now when I write down the formula, 1/2 h parentheses y0 plus yn, blah 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 plus plus 2, and then I have y1 plus y2 plus whatever this is, which I'm going to explain in a moment, plus yn minus 1. Here, the yn, your last one, is going to be this guy there. See? Now, some of you might also be a little bit confused with what is this here? See, why is there a dot, dot, dot? Notice how it's a sum. See, so it's saying it's y1 plus y2 plus dot, dot, dot plus yn minus 1. See? Now, this might be a little bit confusing because of the n, so let me land it a little bit. See, let me land what's going on, whatever. See? Aterrizar la volada. Let me bring it down to earth. Okay, so imagine instead of yn minus 1, focus up here. Imagine I have y5, okay? So what this dot 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 is doing, actually, what the dot 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 is doing is just this. It's a way to write down less stuff, okay? Technically, the dot 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 is this. So you have y1 plus y2, and here goes the dot dot dot. Watch it. The dot 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 is y3 plus y4. And then I finish off with what I had before, y5. See? So the dot 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 is just a way to yo, it's a long string of numbers. I don't want to write them down, but you get the idea, okay? The thing is, when you work with n minus 1, it's yo, basically just take all the y's until the second to last. Ya hasta el penúltimo, ¿cierto? So that's the dot dot dot. So in this case, because I don't have so many y's, technically my equation is just going to end up being, well, the first half remains the same. Vale? So this still remains the same. Here I have a 2. Here I have y1 plus y2 plus y3. And until there, ¿cierto? Because technically, sorry, something I missed to do, the yn we said was my last, ¿cierto? So this is going to change to y4. See? So my last one was y4. That's why I put it like that. My second to last was y3. How do I know it's second to last? Well, because here I put all my y values. Which one is second to last? Y3. So, yeah, that is a slight change in the formula, but now it's a lot more friendly, isn't it? See? So guys, I spent like maybe 10 or 12 minutes explaining like what the formula does, why you use it, because it's an approximation, where you get the y values. But now that you know how it works, boom, you just get it right away. Okay, it's not that hard, but you do need to be familiar with it. Okay, and that's why I insist so much in all of my videos. Dude, get familiar with the formula booklet. Okay, a lot of these problems are not that hard. You just need to know a little bit of intuition and it gets you a long way. Because there's a bunch of people around the world that open the test, they read Trapezodial rule, and they're just like, fuck, I didn't study enough. I have no idea what it is. You know? Okay, that happens to anyone. That it happens to anyone and everyone at some point. The point is, you gotta know this stuff before the test. Okay? And no, you're not gonna know everything by heart. But god dang it, it's not that hard to know by heart the formula booklet. Okay? And more importantly, it's knowing sort of what goes in it. Okay? Point is, you arrive to the test, you read trapezoidal rule, and you're like, damn, I know that's kind of hard, but what tools do I have? And you remember the formula booklet, and you open up the formula booklet, and yes, it looks weird, but now that you watch this video, you understand what is what. You understand that this is first value for y, you understand that this is the last value for y, and these are all the ones that are in between. See? And with that, you're good to go. See? And no, I didn't explain what h is because in this exercise, they give us h. Okay? How do you find h? Well, notice how it's b minus a. Well, that's basically like a is going to be your first value for x, and b is going to be your last value for x, okay? And n is just sort of, well, if n is the last value for y, so in this case, we would have n equals 4, see? So, well, yeah, actually, here they give us h, see? But you can actually find h with what I just told you. So my first value for x is 0, see? So that means in this formula, h equals b minus a divided by n. I already have that the a is 0, see? I said that the b is the last value for x, so that means the last value for x is this guy here, right? 40. So I'm going to have 40. And n, well, n comes from the last value for y. We said that the last value for y was y4, so that means n equals 4. Ah, okay. So 40 minus 0 divided by 4, 40 divided by 4, 10. H equals 10, see? So here they gave us 10. I mean, here they gave us that h equals 10 from the exercise, see? But even if they didn't, we can get it really easily, okay? So guys, really, just if you know the intuition, you're good to go, yeah? All right, that was a very long introduction, but I'm sure some of you don't know trapezoidal rule at all, so I'd rather just be a little more, complete in my explanation, see? Point is, I rewrite my formula to make it a little bit more friendly. I don't have any more n anymore. I have a 4 here. I don't have n minus 1. I have a 3 here. And now I'm good to plug in. See? So we know that h equals 10. This over here is an n. Okay? Just to show that the last value for y is going to be your n. So now I plug in. I'm going to plug it in red. See? So if I go 1/2, I'm going to have 10. y0 we said is 0 plus 0 because of y4, ¿cierto? Plus 2 times y1 is 3, plus y2 is 8, plus y3 is 9. See? So give me a second. I plug all of this in into my calculator, and trust me, you're going to get 200 centimeters. Because it's an area, we write it squared. So the trapezoidal rule, and this is part A, the trapezoidal rule gave me 200 centimeters squared. Then they tell you that it is given that the equation of the curve is y equals 0.04x squared minus 0.001 x cubed with x between 0 and 40. This makes sense because between 0 and 40 is literally from here, from this 0 to this 40. See? Okay, so write down an integral to find the exact cross-sectional area. So again, much like trapezoidal rule helps you find the area, just in an approximation, the integral helps you find the exact area. Okay, so that is a way you can remember it. An integral is for finding the exact area under a curve. The trapezoidal rule is to find the approximated area under a curve. See? And to write down an integral, it's super easy. I mean, and it actually sort of comes from the formula booklet. Let's remember that. Let me make a little bit of space because I did write down a lot of shit. So the part of the trapezoidal rule that is actually the trapezoidal rule is this guy here. See? This is the trapezoidal rule. Okay? Over here, you just have like a normal integral. See? And what's cool about the trapezoidal rule is that it lets you do the approximation. Okay? From an integral. Yeah, it lets you do an approximation, find the approximate area, blah, blah, blah. See? And so when they tell you, yo, write down an integral. See, the first thing you're going to do is write down an integral. This symbol here, see? And we're going to talk about what's B, what's A. Or more of a review because I already mentioned it. So you're going to put down the integral. Let me use a different color just to, because I'm like that. This one, see? So you write down your integral, okay? And we have A and B, see? Now, what did I mention that A and B was? I said that A was going to be your first value for X, and B was going to be your last value of X, see? So, your first value of X, we said was 0, ¿cierto? So I'm going to go ahead and put 0 over here, right, because A is on the bottom, yes. And the last value for X is 40. And another way you can figure that out, by the way, is here, see? You can actually say that this is A and this is B because of the domain that they give you, okay? If they don't give you a domain, just do like negative infinity to positive infinity, okay? It'll work, trust me. So, from 0 to 40, see, that is all my X values that I will be taking for today. All right, and now you see here how you have y dx. So dx is like in respects to what variable you're making the integral, and y is just your function, okay? Okay, so if you have y dx, and actually in the answer key you can leave it like this, but for something that makes more sense to us humans, y is your function, right? So let me go ahead and put a parentheses here. So parentheses is going to be my y. So my y is going to be y equals blah, 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 0.04x squared minus 0.001 x cubed, close parentheses, dx. See? So essentially, in math language, what you're trying to say is, yo, what is the integral of this from 0 to 40 of my variable x? In what equation? This equation. See? All right, so this is quite literally part BI. For part B double I, it says to calculate the calculate the value of the cross-sectional area to 2 decimal places. So basically, this integral we just wrote down is for finding the exact cross-sectional area. And now if we just calculate this integral, we find that area. See, so in other words, we have to solve this integral here. Now, I know a lot of you are probably saying, God dang it, I never understood integrals in class. I don't know what the fuck to do. I get the intuition, I know it's for an area, but what do I do from here? God help me, please. So, guys, check it out. One of the things you walk into the test with, besides your brain and 2 hours of sleep and all those jokes and blah, 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 and the formula booklet, is the graphing calculator. Okay, so get familiar with the graphing calculator, get familiar with what it does, know your tools. Okay, at the end of the day, you face a problem, you look at your tools, you do the best you can. That's all you can do, not just in math, but also in life. Okay, so over here in this TI-84, if you have a different version, I'm sure you also have it, there is a way to plug in integrals. Okay, for the TI-84, you press math. You can do it here. Yeah, so you press math, And down here, it's in the let me try again. You press math, then on the second column from math to num, okay, the second sort of page, you go down to number 5, it says int for integral. All right, actually, I'm sorry, I messed up. But I'm going to leave it in the video because we all mess up sometimes and we're all human. See? Again, get familiar with your calculator because then you can tell when you make a mistake and when you don't, right? All right. For the integral, you press alpha window. So what that does is that it helps you press F2. See? Now notice when you press F2, these 4 little tabs show up, okay? For fraction, for function, for matrix, and for y var, okay? So that means if I press alpha y equals for hitting F1, I open up the fraction menu. Over here, the function. Over here for F3, the matrix, okay? And so there are a lot of different things you can do. See, in this case, we're going for a function, the integral function. Here I have absolute value, uh, you know, the sum of stuff, ¿cierto? But in this case, we are going for integral, see? Actually, you can do the derivative too. So whenever you have to do the derivative, this is a cheat sheet as well. Anyways, enough blah blah. We go to the integral, there it shows up, see? All you have to do now is plug in and plug in property. So here I have my a and b values. See, let's remember that a, the one on the bottom, is the first value of x, so 0, and b on top is the last value of x, 40, okay? Basically, when you do that, you're telling it like from where to where you want to find the area. For example, if here I put 20 instead of 40, what I'm asking the calculator is what is the area from here to here. So you would find the area until you reach the x of 20. Okay, that is what the b value does in this thing. Okay, so again, we leave it in 40 because we're solving this integral I put in this black square. What is my equation? Well, it's right there in front of me, 0.04 x squared, and then we have minus 0.001 x to the power of 3. Don't forget to put dx. What does dx do? You basically tell the calculator in respects to what variable you want to do the integral in this equation, okay? For us, we're pretty much always just going to use dx. Whatever, you press enter, you get this value. See, so part B, part double I, you have 2.13. Wait, I messed that up, sorry. You have 213.33. 3333333. See? Centimeters squared. Now notice they do tell you to answer to 2 decimal places. And so you count 2 decimal places, 1 and 2. Do you round it up or down? It stays the same because 3 is not above 5. So your final answer is actually this. This is your final answer. This is a 1. This is centimeters squared. All right. Last but not least, for part C, we need to find the percentage error in the area found using the trapezoidal rule. Now again, some of you are already thinking, oh my god, fuck, what is percentage error, dude? I never understood percent, dude, oh my god. Guys, get familiar with the formula booklet. I know I'm gonna drive you guys crazy saying that, but it's real shit, dude. I swear it's real shit. You might, if you know the formula booklet well enough to identify the buzzwords, the vocab words that matter, you're gonna read percentage error and you're gonna remember that it's in your formula booklet. You're not gonna remember what the equation is, you're not gonna remember how it works, but you know it's in there. So you're gonna look for it, eventually finding percentage error over here. See? And you're gonna read it, remember a bit what's going on, and it's gonna be good to go. See? So first things first, this E is just like the value of the percentage error, okay? VA, as it says there, is the approximate value of V. And VE, of course, is going to be the exact value. Whoops. Come back, computer. Thank you. It multiplies it by 100% to turn it into a percent. Okay, important. And you might be a little bit confused on what this is. Okay, this is not a parentheses. This is what we call an absolute value. So an absolute value, what it does is that it turns any number positive. For example, the absolute value of 3% is just going to stay as 3%. as I said, any negative turns positive. The absolute value of negative 2% is going to turn into 2%. Okay? Absolute value of 0, it's just going to stay as 0. Absolute value of, I don't know, negative 7 turns into 7. Negative value of 9 turns into 9. You get the idea, okay? 125 positive stays at 125 positive. So whenever it's negative, it goes positive. That is what the absolute value does, okay? So you can basically just find your answer and make it positive, okay? So here, following this equation there, we have, well, first things first, I want to put it in a fraction because it's easier, so I can press alpha F1. And of all these options, the first one gives you a fraction, okay? So the approximate value, what might it be? Well, I did tell you that the trapezoidal rule is for finding an approximation. Okay, so my VA is going to be this. Notice, I'm going to put it in whatever, orange. See, so my VA is 200, right? And my exact, what I calculated with the integral is this, okay? So that means that I'm going to have my VA, we said was 200. My exact, we said was 213.33 divided by 213.33. Go ahead, press enter. I need to multiply by 100%, so I missed that. So just multiply by 100. Okay, so now it's in percent, so it's negative 6.24%. But because of the absolute value, it has to be positive, ¿cierto? So whenever it's negative, just think, okay, absolute value, it has to be positive. If you want, you multiply it by -1 to make it positive, whatever, do your thing. Basically, your answer is going to be 6.248 blah 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 percent. See? So, for your answer, for part C, ¿cierto? You're going to say that it's 6.248, 538, blah, blah, blah. If you do 3 significant figures, you're going to count 1, 2, 3. This one, do you round it up or down? It's an 8, so you round it up. You end up with 6.25%. Exactly as the answer key shows. All right, so that is for this trapezoidal rule problem. Now, guys, I know I spent a lot of time talking in the beginning, but I'm also sure some of you needed that. Regardless, trapezoidal rule usually shows up once per test. It's not that hard, but you do have to know it well, okay? As you can see, it's a very methodological, dude, I don't even know how to say it, but the approach, the method that you use is always the same. Okay, so that's friendly in that sense, and you practice 2 or 3 of these, and they don't usually throw curveballs here. I think the biggest curveball was the percentage error, which again is just a formula that is in the formula booklet. If you're familiar with it, you'll survive. So I think these are 8 easy points. Remember that for the integral, you can just use the calculator and forget about it. See, you can learn how to do it by hand. I don't like to teach it because I'd rather just teach like the easiest thing. I know some of you are probably watching this like a week before the exam, so might as well just give you the easy way out, the quickest way. Use your calculator, dude. There's so many tools in there. You have no idea, man. It's amazing you get to use a graphing calculator for a test, my guy. So yeah, I hope it helped. Take it easy. I'll see you around. All right, and now with number 10, we have probably the weirdest exercise of this whole test. Mainly because of the way it's phrased, of what it says, and it's just a little bit confusing. But let's go piece by piece. So we have that. In a baseball game, Sakura is the batter standing beside the home plate. The ball is thrown towards home plate along a path that can be modeled by the following function, blah. Okay? In this model, x is the horizontal distance of the ball. Okay, so x, as it says here, is the horizontal distance from the point where the ball is thrown, and y is vertical height of the ball above the ground. Both are measured in meters. So my units is meters. Let's not forget that. They tell us that the outcome of the throw is called strike if the height of the ball is between 0.53 and 1.24. Keyword between. Entre, between. Blah, 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 at some point while it travels over the home plate. The length of the home plate is 0.43 meters, which is this here. When the ball reaches the front of the home plate, the height of the ball above the ground is 1.25 meters. Okay, I'm just going to express that right away. So that means that when it's, as it says, when it reaches the front of the home plate, so like right here, the height of the ball above the ground is 1.25 meters. So right at the front of the home plate, we have a height right here of um, height right there is going to be 1.25 meters. Okay, that might be useful later, might not, whatever. Might as well write it down. See? So right there we have a height of 1.25 meters. And the height of the ball changes by a meters as the ball travels over the length of the home plate. So that a meters is right here. See, so notice how basically what it's saying is that if you go down this much, then you must go forward this much. Okay, it's no different as if I tell you this. See? So basically what I'm trying to say is that this is slope. Okay, it's slope or also called gradient. The height of the ball changes by a meters as the ball travels over the length of the home plate. It's basically saying by how much does y change um, when x changes. Okay, so it's going to be slope, it's going to be gradient. We'll see why that's useful in a second. So for part I, we need to find the value of a. So as I was saying just now, technically what they draw here with a, okay, is just slope or gradient, okay? And let me talk a little bit about slope or gradient so that we understand where I'm coming from, see? So let's say you have a line that goes like this, okay? The slope or gradient of this is going to be what they call like the rate of change. See, so I'm just going to say we have the slope, which is the same as the gradient, which is the same as like rate of change, okay? So how is this line changing? Well, as we can see here, um, if it goes forward, I don't know, like 1 unit, see, if it goes forward 1 unit, it also goes up 1 unit, okay? So I'm just making these numbers up, but that's the idea. So your slope, or what they call m, can be modeled by these little triangles. So you see how y changes, and then see how x changes, and that's going to be your slope. When you have a line, okay, and this is going to come from the formula booklet, let me just look for gradient. There it is. Here you have equations of a straight line, see? Which is actually exactly what we're dealing with over here. Up here we have an equation of a straight line. How do I know it's an equation of the straight line? Because this in blue, okay, which I'm now writing in red, is this. Y equals mx plus c, okay? And notice how the c, okay, let me use another color. This c is the y-intercept, and this m, okay, is the slope or gradient that I'm talking about, see? And how can you express m in a different way? Well, you actually have the gradient formula. It's right here, see? Notice how it's y2 minus y1, x2 minus x1. All that's really saying is that you're going to be taking, I don't know, the second point, right? And subtracting it in a way with the first point, okay? That's all it's saying. When it says y2, it makes reference to, it makes reference to your second y value, and y1 makes reference to your first y value. Okay, that's it. That's everything. See? And so a lot of times people hear about slope as rise over run. See? And here it makes perfect sense because when you're rising in your graph, is it your y values or your x values? Ah, it's your y values because it's what's vertical, ¿cierto? And so rise over run is the same as what we're gonna call change in y over change in x. Okay, change in y, change in x. It's the same as what I expressed earlier with the little triangle. Okay, change in y, change in x. Whatever, I'm just explaining it in as many ways as I can what gradient is. And so if we look at the equation that they gave us, ¿cierto? We know that the y-intercept is 2. So we can imagine something that looks like this. We can have this intercept here is 0, 2. And this negative 0.045 is actually going to be your slope. Okay, so this here is negative 0.045 in terms of slope. I'm not saying A is negative 0.045, but for the gradient formula, this right here, it would be. See, it would be. And so notice the many ways I expressed it, see? Ideally, you use 2 points and just plug it in right there. But from here, can I get 2 points? I think if you get creative, you definitely can because they did give you this height. But there's a slightly, maybe more intuitive way to do this. The point is you can try to find the gradient of this triangle here. See? And so for the gradient of this triangle here, well, what's the change in y? And what's the change in x? The change in y is literally just a. And the change in x is right here. Ah, okay. I'm almost done. See? So now that I know that the change in y is a and the change in x is 0.43, what does this equal to? Well, this equals the slope or the gradient. And what's the slope or the gradient? From up here, and from the formal booklet as well, the slope or gradient is m. It's m. It's m. It's m. It's m. What's the slope in this case? What's right next to x, ¿cierto? Negative 0.045, so I can put negative 0.045. And from here, I can solve for a. See? I know that was a relatively long explanation, but it's very important you guys understand where I'm coming from, all that stuff. So for getting a alone, I can multiply by 0.3 to both sides. That means I end up with 0.3 times negative 0.045. And that gives me an a value. Okay, it gives me an a value of negative 0.01935. Okay? If I express that in in my units, it would be meters. And that is quite literally for part A, part I. See? So that is my value for A. In other words, when it passes the home plates, it's gonna go down 0.01935 meters. Okay? So that is my A value. It all comes from the fact that we're talking about slope. Part A, part double I says justify why this throw is a strike. Justify why this throw is a strike. And so there's a couple of things we gotta like really internalize here. See, what is a strike in this context? Earlier they told us that here it is. The outcome of a throw is called a strike if the height of the ball is between 0.53 and 1.24 while it travels over the home plate. See? Okay, so basically I need to see if somewhere along this line, ¿cierto? I am between that height, ¿cierto? 0.53 and 1.24. And so what we can do here, okay, because we know that the height of A, ¿cierto? How much it changes as it travels over the home plate is 0.01935. And the height when it first reaches the home plate at its front is 1.25 meters, as they told us here. What you can actually do is that you take, actually I'll do it up here just so that there's more space. What you can actually do is take that 1.25, which is the height above the home plate, okay, and subtract it by A, 0.01935, and see what value you get, okay? And if this value is between what they told us, then it's going to be a strike. If it's not, it's not a strike. See? So how much does this give me? This gives me 1 point. Actually, let's just double check. Minus this. Gotta make sure it stays negative though. Yeah, it gives you that. Okay? So 1.23065. So technically what I just found with what I just did was that the height of here, that I'm going to put in blue as well, the height of here is 1.23065 meters. See? And so is this between 0.53 and 1.24? Yes, it would be. And so for part for part A, double I, what you would express is that 0.53 is less than 23065, which is the value we just got, okay? Which is less than 1.24. Okay? So this is when they tell you that it's between, okay? You are literally expressing it right there. You're putting it between both numbers. It would be between. And so this is a way, and notice keyword, it does tell you to justify. Okay, so when it tells you to justify, put as many like math languages into it that you can. This is one way to put it, but you can also just say 1.3065 is between 0.53 and 1.24. Okay, this is another way to answer. It's literally the same, just that one of them has math symbols, the other one doesn't. Big fucking deal, okay? So blah blah blah, it is between, make sure that you're right, therefore it is a strike. Okay, put a smiley face so that they give you another point. Anyways, that is for parts AI and parts AI. And then it gets a little bit juicy. What they tell us is that on the next throw, Sakura hits the ball towards a wall that is 5 meters high. Damn, towards a wall that is 5 meters high. They tell you that the horizontal distance of the wall from the point where the ball was hit is 96 meters. So, in other words, we have 5 meters for vertical or for high. See? Then they tell us 96 meters for horizontal distance. Okay? That's the main intuition we have to draw from this. The path of the ball after this hit can be modeled by the function blah. See, blah being this whole thing. All right, cool. In this model, h is the height of the ball above the ground, and d is the horizontal distance. Ah, okay, so d for horizontal distance, h for height or vertical. See? Ah, so now you start connecting these dots. It's important to highlight the buzzwords, as you see that I put in yellow, because now it's very easy to see that height is for high, or just 5 meters, okay? And that horizontal distance is for this 96 right there. We're going to see in a moment how it makes sense, but that's the idea I want you to get from this, okay? So they're both measured in meters. Important to keep your units in mind. Determine whether the ball will go over the wall. Justify your answer. Okay, so technically what we can do here, right, is that the wall, ¿cierto? How far away is it? It is 96 meters away. See? And so what we can do is that we can take this equation, ask it, yo, when you're 96 meters away, what is the height of the ball? And if the height of the ball is bigger than 5, that means it goes above the wall. If it's not bigger than 5, then it does not go above the wall. See? Actually, if I go ahead and graph this on Desmos, see, just so that we really understand what's going on. And yes, you can do this in the test just with your graphing calculator. It's just that Desmos is a lot quicker, so I'd rather show it here. You're going to have something that looks like this. Is that right? Negative blah, 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 plus blah, 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 plus blah, blah, blah. See? Ah, yeah. And so notice, this is how the ball goes. So Sakura hits it, flies all the way over here, and what we're trying to see is, okay, when it's at 96 meters, is it taller or smaller than what the wall will be? So technically, if I go ahead and graph that, what I just did, what you would be asking is, okay, so the ball travels like this, and you need to see at 96 meters, okay, so you need to see at this 96 right here, you need to see the height of this ball, okay? And I'm just going to show it to you for now graphing, and you can find your answer graphing. So I'm just going to show a different way, but just so that we're all on the same page. Here you have that 96, and the height is 8.34. And so basically, here I have the point 96, comma 8.34. And what you conclude is that it flies over the wall because the wall is just around 5 meters high. Okay, so that is what's going on. This is like the graphic representation. Here you have the wall. In red is the ball, of course. And as you can see, it goes over the wall. Okay, it goes over the wall because right at 96, where the wall is, the height of the ball is 8.34, so it flies over it. See? So this is one way to answer, actually. You can literally just graph it and say, like, yo, at this point, it goes above it. Chill, take it easy. The other way that most people would probably do is like, okay, so what you're trying to do, or the information you're going to have, is that you imagine this graph and you know that you need to ask the calculator at 96 meters, what is my height? Okay? And yes, you can graph it. I know with Desmos it was really quick, but you can use graphing calculator with y equals. Okay, just so you know, it's an additional tool you can use. You can just put it in here. That it? Um, but maybe a more intuitive way is that you know that the ball is at 96 meters. You want to see what's the height of the ball at 96 meters. So you're going to take your function, okay, and you're going to go ahead and plug in. You're going to plug in 96. So h 96. So what you're saying here is when d is 96, what is h? Okay? When the distance is 96 meters, what is the height of the ball? That is what I'm expressing is with h parentheses 96. So I'm going to go ahead and put negative 0.01 96 squared plus 1.04 96 plus 0.66. Okay? And just go ahead and pop that whole thing into your calculator just so that it doesn't take as long. Yada, yada, yada. Kapow, 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 kapow. And kapow, 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 kapow. And there is the 8.34 that we saw earlier, actually. And so the height at 96 meters is 8.34. And all you have to do is say that 8.34 is bigger than 5. See? Therefore, the ball goes over the wall. And that, ladies and gentlemen, is number 10. I don't think it's incredibly hard, but it is super confusing. In fact, the first time I read it, I was like, what the hell is going on? But once I identified that A, or better said, this little triangle here, makes reference to slope, everything just kind of like, it flowed very quickly, very easily. Okay? So, you guys, a lot of times, you're not gonna, some exercises don't make sense right away, okay? And they don't have to make sense right away. Some of these exercises are really fucking hard. In fact, I think this one, it's not the hardest, but it is the most confusing one. See? I mean, there's so much text. It's literally too much text, okay? So just so you know, some of these exercises are confusing. Okay, none of you don't have to read an exercise and immediately know what to do. Okay, that's not realistic. We got to be realistic with ourselves. But I think it is important that you can read an exercise and sort of know like the general direction. Okay? And for me, it took me a bit to find the general direction until I noticed the slope thing. Okay? So that's also why I explained the slope thing in like 4 different ways, because it's very important that we have it clear, we have it as a tool in our minds for when we face an exercise like this. So anyways, that is how you solve this. I hope it made sense. I hope you feel better, and I hope you have a great day. That is for number 10, and I'll see you around. All right, so now for number 11, we have that vertical posts are to be placed around the outer edge of a children's park. Each post is formed from a cuboid with a right square-based pyramid on top. Kapow, that's a lot of buzzwords. It's this guy here. The cuboid part of the post is a machine made such that its width, and hence the width of the pyramid, is exactly 20 centimeters. So this 20 is right there, and the length from the apex of the pyramid, A, or in other words, the tallest part of the pyramid, to any corner of the base of the pyramid is 14.6 centimeters. That's this guy here. So for example, from A to C, it's going to be 14.6. From A to B, it's also 14.6. Okay? From A to E as well, from A to D as well. That it? So that is what it means by the 14.6. But, ooh, they put it in bold. It's gotta be important, eh? But this is only accurate to the nearest tenth of a centimeter. The post is shown in the diagram. For part A, we need to write down the upper bound and the lower bound for the possible lengths of the edge AC. So, for part A, we are talking about the number 14.6 to the nearest tenth of a centimeter. See? So we have this 14.6. First things first, what the heck is a tenth? Okay, and this is the sort of thing you can Google and find right away, but here this 4 is going to be your ones, and this 6 is going to be your tenths. Okay, so if it is only accurate to the nearest tenth of a centimeter, that means that your upper and lower bound have to play around with that tenth. Okay, so there's going to be two sort of like veins. See, you're going to have the lower bound, of course, and you're going to have the upper bound. See? So think about the lower bound as the smallest you can get and still estimate it to 14.6 to the nearest tenth. Okay? So, for example, 14, I'm just going to make it a little bit smaller. I'm going to have 5.9. See? So you round it. Do you end up with 14.6? Yes. 14.58. You round it. Do you end up with 14.6? Yes as well. Guys, what's the breaking point? From 5. From 5 to up. From 5 up, right? You stop rounding up. See? Example, you have 16. I tell you to round it, you end up with 20. You have 15. I tell you to round it, you end up with 20. 14. I tell you to round it, you can't round it, you leave it as 14. See? That is because the breaking point is from 5. Okay? Whatever. We're about to see it in action. It's going to make a little bit more sense now. So, 14.57. Do you round it up? Yes. 14.56. Do you round it up? Yes. 14.55. Do you round it up? Yes. 14.54. Do you round it up? No. And there is my lower bound, ladies and gentlemen. Not that hard, eh? So for the lower bound, it's going to be 14.55. See? For the upper bound, it's very similar, but it's also a little bit, maybe a little bit more confusing. See? So for the upper bound, I'm going to make it bigger just by a little bit. See? So I'm going to have 14.61. Do you still round it to 14.6? Yes. 14.62. Do you still round it to 14.6? Yes. 14.63. Do you still round it down to 14.6? Yes. 14.64. Do you still round it to 14.6? Yes. 14, and let me make a little bit of space. 14.65. Do you round it up or down? This way round it up. So from here, kapow, it's not. See? So your upper bound is actually technically between the 6.4 and the 6.5. It's just a little bit harder to find which number it is, right? And so here it gets, here it just gets kind of weird, okay? So technically, you would still round it down if you have 14.64, I don't know, 8. You still round it down, see? What if you have 14.649? 14.649, you also round it down, see? And so what is the closest you can get to 14.65 and still round down? Well, you guessed it. It's going to be 14.64 9999999999999. How's my German? All right. So technically, this is the closest you can get and still round it down. See? The problem is that you can't really express that, and you actually have to express it as this guy here. And I know some of you are already telling me, what the fuck? But I'm going to tell what the fuck to you back, because if you look at the answer key literally tells you from 14.55 to 14.65. Okay? It's pretty shitty. Okay? It's pretty shitty, but what I'm trying to express is actually over here, ¿cierto? So here, it's like the number right before 6.5, so you can leave it as 14.64999999. See? And so technically, you can leave this as an equality, as the answer key says. You can say, okay, so it's from 14.55 less than or equal to blah, 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 14.65. See? So that would be a way to express what I just put. Or you can notice the following. Whenever you put this 999999999, it's technically the same as reaching 14.65. And it's so much so that in the world of math, if you put 0.999999999999999 in your calculator and press enter, it gives you 1. Your calculator basically tells you, dude, it's so close to it, fuck you, it's basically there, it's just 1. See? And this is no different, ladies and gentlemen, if I put 14.649999999999, you still get 14.65. See? And so, point is, you can express it in two ways. You can either do the equality here, which makes a lot more sense to me, or you can say that the lower bound is 14.55 and the upper bound is 14.65. See? So you either say that the upper bound is this and that the lower bound, okay, and that the lower bound is that. Whatever floats your boat, I just really needed to explain the thing where the 99999 ends up being 65. Okay, that is the thing you needed to understand in this exercise. That's that. Okay, so that is lower bound and upper bound. Ladies and gentlemen, we move on. They tell us that point H is the midpoint of BC. Okay, midpoint of BC. Determine the upper bound and lower bound for AH, the slant height of the pyramid. Okay, so now it gets a little bit more interesting. See? First things first, because H is the midpoint of BC, that means the distance from B to H and the distance from H to C is the same. That's why I put a stick on both of them to signify that they're the same distance. And because I know that from E to B, for example, is 20. See? That means from B to H is 10, and from H to C is also 10. See? Now, the upper and lower bound again for AH, see, has to do with the fact that this 14.6 is either, for part A, it's either 14.55 for lower bound or it's 14.65 for upper bound. It's one or the other. And so we need to see how these two sort of versions, okay, are going to affect my calculation for finding AH, okay? And so for AH, again, I'm going to end up with two versions. Notice how here I did lower bound and upper bound. I'm going to end up doing the same for part B. So for part B, I'm going to have the lower bound version, so lower bound version, and then I'm going to have the upper bound version, okay? Now for both exercises, the approach is fairly the same. Because we need to determine AH, the slant height of the pyramid, the key thing here is to think in triangles, okay? So if you think in triangles, you're going to end up finding, well, you can find this one here, see? The one that I'm putting in blue, this is a triangle that you can consider. And so that triangle has points A, H, and C. So I can go ahead and put, for both, I'm going to have A, following my diagram, I have A, then I have H, then I have C. So it's going to be A, H, C. And for the other one as well, I'm going to have A, H, C. And now go ahead and put everything you know about that triangle into your graph. So for the lower bound version, we have 14.55, okay, which is AC, so from A to C. So 14.55. Or for the upper bound, we have 14.65. Okay, what else do I know? Well, I applied the midpoint information that they told me. So from H to C, it's 10. It's exactly 10. See? So here's 10, here's 10. How do you know that there's no lower or upper bound here? Well, because they tell you that, as I highlighted before, the width of the pyramid is exactly 20, so I can cut it in two and it'll be exactly 10 and exactly 10. Okay, so that is, there's no cheating there, okay? What else do you know? What else do I know? What else do I know? Well, because it is a square-based pyramid on top, then I have right angles. Well, they actually put a right angle here. Just let me zoom in a lot. They put me a right angle right there. See? So that means I have a right angle right here. Ah, okay. So now this triangle is starting to look very friendly, doesn't it? So I have a right angle here. I have a right angle there. Guys, what are my tools for right angles? For right angle triangles. I have the famous Pythagorean theorem. See? And so Pythagorean theorem, what it tells me, I'm just going to write it here real quick. Pythagorean theorem I probably wrote that wrong, but I really don't give a fuck. The Pythagorean theorem is a squared plus b squared equals c squared. Okay, and the most important thing for the Pythagorean theorem that you need to keep in mind is that c is the long side. And c, as you can see in the formula, c is alone in the equation. Equation, formula, whatever. See? So c is the long side. If you want to get really fancy in math language, it will be the hypotenuse. Okay, in fancy math language, it's hypotenuse. Okay, so c is the long side, and you define c, you define a, you define b. These are all sides. Okay, so technically from here, I need to find x. Right now, is just focus on the long side. See, for lower bound, which one is the long side? The long side is this one here, 14.5. What is another way to identify the long side? It's whatever is opposite to your right angle. That's another way to find the hypotenuse is whatever is opposite to your right angle. So that means I can write 10 squared plus x squared equals 14.55 squared. See? And if I leave x alone, it would actually be x squared equals 14.55 squared minus 10 squared. And if I go ahead and apply the square root from here to get, the squared alone, so if I do square root here, square root to both sides, that means this goes away with this, and I end up with x equals that. See? So for lower bound, I'm going to have that x equals, we're about to find out, x equals the square root of 14.55 squared, oops, minus 10 squared. See? So that means the lower bound is, I'm just going to write it. See, the lower bound is 10.5689. If I'm not mistaken, let me double check. Yes. And if you want to do significant figures, you count 1, 2, 3. This one to the right, do you round it up or down? It's a 6, so you round it up. It's the same as leaving 10.6. Don't forget units. I think it's centimeters. Yes, it is centimeters. See? So the lower bound is going to be 10.6 centimeters. See? For the upper bound, the approach is literally the same thing. We're going to have that 10 squared plus x squared, okay, equals 14 points. It wasn't 6, it was 6.5. So hey, look at that. We all make mistakes. If you noticed, good job. If you didn't, don't worry. 6.5 squared. So again, x squared equals 14.65 squared minus 10 squared. If I go ahead and apply the square roots, this goes away with this. X is going to equal, let me just show you in the calculator because why not? X is going to equal, kapow, yeah, 10.7061. See? Three significant figures, same idea, 1, 2, 3. This guy to the right, it's a 0, so you leave it as it is. You can write x equals 10.7 centimeters. See? So the this would be the lower bound. Okay, for the for the slant height of the pyramid, and the upper bound would be 10.7. See? So that is just to be super clear, this would be the lower bound, this would be the upper bound, okay? For what? For the slant height. See? Alright, so that is for part B. Then they told me that for the post to be safe for children, the angle between the slant height and the base of the pyramid must be less than 22 degrees. We need to show that the post is safe for children and justify our answer. See? So, the hard part here is really identifying by what do they mean when they say the angle between the slant height and the base of the pyramid, okay? So, where is that angle? An angle is always going to be between two lines. So that's why they say between. Between what? The slant height, which is this guy here, that cuts right across like that. Okay, that's my slant height. And the base of the pyramid. See? The base of the pyramid is basically como just this guy here. See? That is the base of the pyramid. And well, technically, to make an angle in this context, I actually made a small mistake there. The base of the pyramid is this whole thing. See? And so, what line is convenient to put there? This line here. See? So you're trying to find the angle that is formed right there. Okay? And so here, there's actually another triangle that can form. Okay? There's a couple ways to think about it. The one that makes most sense to me is to put a triangle that goes like this. Kapow, kapow, kapow. Now, what do you know about that triangle? See? Well, you know the slant height, ¿cierto? That has two versions. You have the lower bound slant height, ¿cierto? For 10.6, and the upper bound slant height for 10.7. So that gives me, let me just redraw this over here, see? It's the same triangle, the same shape. Okay, you have this angle here. I have the slant height, so I have this that the slant height is either 10.6 or 10.7, see? What else do I know about this triangle? There's a 90-degree here, because it goes straight up from the apex to the base of the pyramid. And you know that this is 10. Why do you know that it's 10? Because of this 20 here, that means half of it is going to be 10. The other half is also going to be 10. See, it's no different than the midpoint we talked about earlier. That is all I know about this triangle. And I need to find that this angle here, with the lower bound or the upper bound, okay, is safe for children because that angle is less than 22. So basically, you need to find this angle here from there. See, from this diagram here, using the lower or the upper bound, whichever makes more sense. See? So, we're going to go for both versions, see, using the upper and the lower bound, right? There's a lot of different approaches here. Okay, you can use sine rule, cos, there's a lot of shit that you can do, okay? I'm just going to use the one that is most direct, but props to you if you find another one. There's a couple ways to do it. You do you, okay? From here, usually, especially if you already have two sides, that it, you can do this thing that is called SOHCAHTOA. See? So notice how in trig, the tools you have are sine, cosine, and tangent, okay, for triangles. The way to remember them, and I don't know why some people don't have it very clear. I guess not all schools show it in depth, but sine, cosine, and tangent, and I guess it depends on your language as well, see? But sine, cosine, and tangent, you can remember sine as so, you can remember cos as ka, and you can remember tan as toa. Okay, this is just the kind of thing you have to remember. SOHCAHTOA, sine, cos, tangent. SOHCAHTOA. It even kind of rings, see? SOHCAHTOA. But remember it, okay? This is the kind of thing that if you remember, it goes a long way. Why? Because for sine, it's a remember that you use sine when you have opposites over hypotenuse. Is that you use cosine when you have adjacent over hypotenuse. And that you use tangent when you have opposites over adjacent. See? So in this case, I have a triangle that looks something like this. Well, of course, I have two versions. Here I have 10 degrees here, then 90 there. I need to find this angle here, see if it's below 22 or not. And here we're going to have the lower bound version, okay? For the lower bound version, you have 10.6, okay? For the upper bound version, we have literally the same case, 90 degrees, a 10 goes here, a 10 points. Actually, fuck, I messed up. The lower bound. Fuck, no, because this is the slant height. Wait, fuck. Yeah, see, yes, the lower bound is 10.6, the upper bound is 10.7. Apologies, I just wasn't sure for a second. So here it's going to be 10.7. Here it's going to be 10.6. Okay, cool. And we're going to find in either of these cases whether this theta angle is less than 22 or not. See? And so remember that SOHCAHTOA is from the perspective of the angle. See? So from the angle, do you have the opposite or hypotenuse? Do you have the adjacent or hypotenuse? What's going on? See? So really focus on this guy here. From the angle of the from the angle of the angle. From the perspective of the angle, see? This 10, what is it? It's the adjacent. See? So this 10 is going to be adjacent. All right? Because it's right next to it. Now this 10.6, you might be saying, okay, that's also right next to it. Aha! But this thing that's also right next to it is what we call the hypotenuse, okay? So that is an important distinction. The hypotenuse is always the hypotenuse, okay? The adjacent can't change relative to the angle. The hypotenuse is always the hypotenuse because the hypotenuse is the long side of the triangle. It's what's to the opposite side of your right angle. See? So we're going to apply that for both cases. This is hypotenuse. This is adjacent. Technically, this here would be opposite. Okay? Just so you guys know, that is how you treat SOHCAHTOA, adjacent, hypotenuse, opposite, all that shit. See? So for this angle here, we're going to say, because it's adjacent over hypotenuse for cosines here, so right now we're only looking at this guy here, we're going to have cosine of my angle. Let me do lower bound first, so up here. So cosine of my angle is going to equal adjacent over hypotenuse, so 10 over 10.6. See? Now, you need to get this guy alone, see? And so let me make a quick example. Let's say you have 2x equals 4, see? And I say get x alone. What is affecting x right now? X is being multiplied by 2. So to get x alone, you divide. Why do you divide? Because division is the opposite of multiplication, and right now I'm being affected by times 2. You do the opposite, you divide by 2 to both sides. That is how you get x alone. That is how you reach that x equals 2. So in this case over here, it's no different. See, this theta is being affected by cosine. What is the opposite of cosine? Inverse cosine. What is the inverse operation to multiplying? Dividing. What is the inverse operation to cosine? Cosine inverse. So here you can apply cosine inverse, cosine theta, and what the magical thing about that, which I'm about to show, okay, you gotta apply to both sides. This is no different than multiplying or dividing. You gotta do it to both sides. What cosine inverse does is that kapow kapow. What happens? You end up with theta equals cosine inverse of this whole thing over here. Okay? And so for the lower bound, we're gonna see that cosine inverse, we press second cosine. It's a fraction, so let me just do alpha alpha y equals to reach f1. 10 divided by 10.6. Okay, so my angle here is 19. So for the lower bound, is it safe for children? If my angle is 19.37, yes, it is safe because it must be less than 22. So for the lower bound, it checks out because it's less than 22. See? For the upper bound, it's the same shit. See? So for the upper bound, you're going to do cosine of your angle equals adjacent over hypotenuse. So it's going to be 10 over 10.7. So the process is the same. You do cosine inverse because cosine inverse is the opposite of cosine. It helps you get rid of the cosine, quite literally. So you're going to end up with 10 divided by 10.7. Yeah, you guys get the idea by now. This goes away with this. You end up with just theta. See? Theta angle equals that. So pull up the same thing, just that instead of 0.6, we have 0.7. Here, for the upper bound, the larger number, you end up with 20.839. See? Close enough. If you round it up, if you put all the decimal places and not do the significant figures like it did in part B, notice how in part B I put 10.6. If you use all the values here and all the values there, you end up with a little bit closer to what the answer key says. But hey, if you use significant figures, it's just fine, okay? You end up with basically just angle of 20.9. See? The conclusion of this is the same. It is less than 22 degrees. The post is safe. So what would you say? You would say for lower and upper bound, we have a safe post because the angle never passes 22 degrees. And then you put the examples of 20.9 degrees is the largest it got. See? There's a lot of different ways to answer this, but basically you have to write a small sentence like it's never bigger than 22 degrees. Keywords, the post is safe. See? Put that somewhere. Justify your answer. How did I know I had to write a sentence? Because it says justify your answer. So basically you just, if you get really, really mathy about it, you would put something like this. 20.9 is less than 22. Okay? And you could even put the other one as well. You can put 19.37 is less than 20.9, is less than 22. They never pass 22. Okay, that's the whole idea. All right, guys, that is for number 11. I hope it helped. All right, and now we go ahead with number 12, which for some reason on a specific day, the speed of cars as they pass a speed camera can be modeled by a normal distribution. What the heck is that? With a mean of blah, blah, blah. See? A speed of blah, blah, blah is 2 standard deviations from the mean. Part A, find the standard deviation. All right, so let's talk a little bit about what a normal distribution is, what a standard deviation is, and all that good stuff. See? So basically, a normal distribution talks about how your data is like, well, distributed, how it looks like, okay? And so a normal distribution looks like what they call a bell curve, okay? It looks like this. It happens a lot in real life, and it's fairly interesting. For example, if you look at the weight of all babies when they're born, and you take like, I don't know, 1,000 babies, you're gonna end up with a normal distribution, okay? If you look at like, I don't know, the height of maybe like animals or whatever in some species, you would probably end up with a normal distribution. See, and so that's why it's a normal distribution. It shows up like almost everywhere, and it's kind of cool, and it has some properties, and we're about to talk about it. So right down the middle, you will have the mean, okay? And the mean, you express it by using this symbol here. So this is the mean, okay? When they talk about standard deviations, okay, that is, think about or associate standard deviation to spread, okay? So like 2 spreads over, you find 75.7. So if my mean that they tell me is 67.3, that means one standard deviation over to the right and another standard deviation to the right is going to give me the 75.7. Okay? 75.7. Okay, what do I know about these 2 points right next to it? Well, I know that one next to it is going to be mean plus 1 standard deviation, and another one is going to be the mean plus 2 standard deviations. Okay, so that is for this guy here. Got it? In other words, I can say, okay, so basically, I can have, well, I can do standard deviation plus 2. I mean, sorry, 1 mean plus 2 standard deviations minus the mean is going to give me 2 standard deviations. See? Following this graph here. So, in other words, I'm going to have 75.7 minus 67.3 is going to give you 2 standard deviations. Okay, cool. So 75.7 minus 67.3 gives you 8.4. 8.4 equals 2 standard deviations. Divide by 2 to get standard deviation alone. Standard deviation is equal to 4.2. 4.2 what? Kilometers per hour. Okay? Oh, and that's also something I forgot to mention. When they put this negative exponent, okay, remember that a negative exponent, for example, x squared stays as x squared, x to the power of negative 2, okay, turns into 1 over x squared. So what does the negative exponent do? It just sort of like flips it, okay? So when you have kilometers, whoops, sorry, 1 second. So when you have kilometers, h to the power of negative 1, the negative 1 flips it, so this is the same as saying kilometers divided by h, which is the same as just saying kilometers per hour, okay? Which is what we're used to looking at. I don't know why the me expresses it in a weird way, but whatever, okay? At least for me, it's weird. So for part A, we already did it, okay? This is part A. Just finding the standard deviation, doop-de-doo, all fine for now. Then they tell us that speeding tickets are issued to all drivers traveling at a speed greater than 72 kilometers per hour. And we need to find the probability that a randomly selected driver who passes the speed camera receives a speeding ticket. So in other words, we need to find 72. This is what we have to do. Okay, so anyone greater than 72 kilometers per hour, what's the probability that they get caught? So where is 72 in my graph? 72 is probably like around here. See, I'm not so sure, whatever, it doesn't matter. Okay, so let's just say that this is my 72. See, so anyone traveling at speed greater than, okay, is going to get a speeding ticket. So that means all these guys here get a speeding ticket. And we need to find the probability. See? Now, some of you might be thinking, what the hell? How are you going to find the probability here? Okay. Here's something interesting, you guys. When we talk about probability, it is going to be the area under the curve. So whatever is the area under the curve is going to be the probability of what you're looking for. So this thing I just colored in green, technically if I find the area of this figure here with the curve and everything, it's going to be the probability of someone getting caught with a speeding ticket, okay? I mean, that someone selected a random gets caught, because someone selected a random is all this area here. We're about to find out how responsible or not our community is. All right? So, it's very clear what I have to do. I need to find the area under the curve. Now, some of you are probably thinking, okay, cool, how the fuck do you do that? See? Guys, the day of the test, I know I say this in every video, but damn, it's so important. You guys have no idea. The day of the test, you walk in with your pen, your pencil, 10 minutes of sleep, your brain, your graphing calculator, your formal booklet, and whatever. The motivation and everything you've learned the last 2 years. See? So really get familiar with all of those tools. What do they offer? What can you do? What can you not do? See? You gotta know that the graphing calculator has a whole ass section, and I'm dead ass on this. It has a whole ass section on distributions. See? So it can help you to calculate like area under the curve. It can help you if they give you an area and you need to find like the x values that go associated with it. You can find a lot of shit here. Okay? So, where is it? It's right above vars where it says distribution in blue. So how do you hit the blue button? Well, you first hit the blue button, unironically, press vars to reach distribution. Now here are a couple tools. The only ones you're pretty much ever going to use, in my opinion, are normal PDF, CDF, and inventory normal. See? Let's talk a little bit about the intuition of each. I'm not going to go too far into it, okay? But I think it is important for you guys to know, like, just what is going on. See? So for normal PDF, the intuition I need you to have, and if I open it, see, you're gonna see it's for the probability of one x value. See, so here you put one x value. That U symbol is the mean. See, as I showed you here, this guy here. So that U symbol is the mean. That other symbol is the standard deviation, and paste is just enter. Okay, so for normal PDF is for finding the probability of one x value. Like if they ask you, what's the probability that a randomly selected guy drives at 50 kilometers per hour? Okay, that's this guy here. See, so that would be a context for normal PDF. Yeah, normal CDF, the one that you're gonna end up using most of the time, as we can see, kapow, kapow, kapow. See, it asks for a lower and an upper, the same mean, the same standard deviation. So this is the probability of an area, okay? So here you can see that it has -1 to the power of 99. Basically, what that is saying is that this is -1,0,0,0,0,0,0. See? You can think about it as like negative infinity, okay? So yeah, in that case, it would be saying like, okay, from negative infinity up until, I don't know, here, you find the area, okay? In this case, we're gonna go from 72 to infinity. We're about to see how that works, see? But I do want to show you all the tools. Let me finish up with inventory normal, and I will be right with you, sir, see? So over here, inventory normal, you can see that they give you an area, okay? And you find the x value. So plug in area, get x value, okay? This is my cheat sheet. This is the very intuitive way to understand it. Whatever, see? I just hope it helps you. There it is. So in this case, we need to find the area of the stuff in green. So from 72 up until positive infinity. Okay, cool. So now I know that for CDF, or just looking around my calculator for a bit, I go ahead and remember, yeah, I use CDF because it has a lower and upper. So what is my lower? 72. From 72 up until infinity. How do you express infinity? Okay, some of you might want to get fancy and do what the calculator had, which is like 1, then like the E thing, and like 9999. Okay, sure, you can do it that way. But just think about upper being like just a very big number, okay? So go ahead and put a very big number, okay? It'll work. It'll work. It's just Upper is basically infinity right now. See? You just put a huge number, it'll work, yeah? What is the mean? They gave us the mean. The mean is 67.3. The standard deviation, I got it from part A, 4.2. Go ahead and paste. There it is. See, so this area in green, this is for part B, is 0.1315. 1315. Whatever, you can write the whole thing. So 1559, okay? Now, if you want to express it as a percent, you go ahead and multiply it by 100 and add a percent symbol. So it's going to be 13.15 blah 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 9%. And if you'd rather stick to significant figures, if you're that kind of guy or girl or whatever, you count 1, 2, 3, the third one. Do you round it up or down? You look at it to the one on the right. Is it 5 or above? It is 5 or above, so you round it up. You can also leave it as 13.2%, okay? Whatever, that is part B, who cares? Then they tell us that it is found that 82% of cars, so here they're giving me an area, so let's remember that area is probability, of cars on this road travel at speeds between p kilometers per hour and q kilometers per hour, where q is bigger than p. This interval includes cars traveling at a speed of 74 kilometers per hour. Show that the region of the normal distribution between p and q is not symmetrical about the mean. Okay, so this part right here is weird as fuck, okay? Basically, what they're trying to say is the following. Let me just make a little bit of space so I have more to play with and I can explain better. Yeah, so we said that the mean is 67.3, okay? So, and this part is really, really weird, so just really try to pay attention here. We need to show, with the information they gave us, that the area between P and Q is not symmetrical, see? If it were symmetrical, okay, let's first go with the case where it is symmetrical, see? So if it were symmetrical, you would have P here and Q there because, well, because we know that P is less than Q, so Q is bigger. And if it were symmetrical, you would have something like this, something like that, okay? And you would know that this is, I don't know, 15%, and therefore if it's symmetrical, over here, it is also 15%, okay? And notice, because it says symmetrical about the mean, so like you cut down through the middle here, 15% on both sides. That is what it means when it is symmetrical about the mean. In this case, we need to show that it is not symmetrical about the mean. So it's a lot more harder to prove, but we're about to see what it means, see? So not symmetrical would be a case where it's just a little bit to the right, let's say. Let's say it's just, I don't know, this Q is maybe more over here, okay? So we would have still that same 15%, but over here I would have, I don't know, 25%. There it would not be symmetrical about the mean because one area, and this is the key idea, it's not symmetrical because one area is bigger than the other. Okay, so all you need to do is compare from the mean to, like, you know, one of the edges. Okay, so compare from here to here or from here to here and work with that. Okay, now you know one key important information. See, so one key important information is that you know that the area between P and Q is 82%. Okay, so you know that, whatever, I'm just gonna say P percent, okay, and Q percent. Yeah, so you know that P percent plus Q percent is 82%. Okay, and so if it were symmetrical, then that means that P percent equals half of that, so 41, and that Q percent equals half of that, which is 41% as well. See? So this is a case where it is symmetrical. See? So basically, if I find these percents of the areas under the curve from the mean to one of the edges, and they're not 41%, that is a way to prove that they're not symmetrical about the mean. If they are symmetrical about the mean, both of them should be equal. Both of them should be 81 because it's half of 82, which is the 82 that they give me. Okay, now it's starting to make a little bit more sense. So what tool can I use? Well, like, do tell me key information. This interval, the 82%, includes cars traveling at a speed of 74 kilometers per hour. Now, this 74, you guys, is it bigger or smaller than the mean? Ah, bigger than the mean. See? So that means because it's bigger than the mean, we're talking about Q. Well, because Q is bigger than P, and we need to see if they're in between the mean or whatever, blah, blah. See? Okay, so technically here, you can sort of like say, okay, so this Q is like the area, but you can pretty much say that Q is going to be this 74. See? I mean, it's not that, it's hard to explain, okay? But point is, if you go ahead and plug in 74, you can draw some conclusions. Let me just pull up what the calculator says and it'll make more sense. See, this is hard to explain, but I'm trying my best. So pull up normal CDF. The lower is going to be the mean, ¿cierto? And then the upper is going to be 74, okay? Well, the mean is still 67.3. The standard deviation is still 4.2. So basically, we're saying, okay, from the mean, right, to 74, wherever it is, okay, how much is that? See? So you go ahead, you press paste, you end up with 44, okay? And so technically, if, here's the thing, here's like the big idea. If from the mean to 74 points, how much was it? 74.6, ¿cierto? No, just 74, sorry. If from the mean to 74, the area is 44%, and let's remember the total is 82% from over here, ¿cierto? From there, 82. Then the area to the left, okay, is going to be, well, this 88 minus that 40, sorry, this 82 minus the 44%, 38%. Is going to be 38%. Therefore, not symmetrical. If symmetrical, should have been 41% each. See? And that, ladies and gentlemen, is enough for you to conclude and answer part C. Okay? Now, although technically the video is over, this last part is so fucking weird, I'd rather just explain it again one more time. Okay? So again, if they're symmetrical, if these areas are symmetrical, both sides should give me 41%. Okay? The fact that I find a different area from 41, in this case 44, means that it's not symmetrical. See, it's like a little bit more to the right. See? Now, how did I know that you need to plug in 74? Well, because they tell you that this interval includes cars traveling at a speed of 74. See? And although you might tell me, okay, but you don't know if Q reaches here or there or here, well, you know at least how far it goes. You know it goes at least until 74 or more. Okay? And so if you play around with the fact that it reaches at least 74, you can go ahead and plug in 74 for a normal CDF. See? So I know some of you might be thinking, again, the fact that it includes cars traveling speed of 74, like you still don't know what Q is, right? Q could technically still be 80. Okay, but just work with what they give you. They tell you that this interval includes cars traveling the speed of 74. Yeah? You know that Q reaches at least 74. Okay, so you find the area from the mean to 74, and that already makes it not symmetrical. Then that is all you need to know. Okay? That is all you need to know. So basically, think about the areas. See, if it's symmetrical, they both have to be half of 82, in this case 41. And so the moment we went over 41 by reaching 44 is the moment we said, fuck you. That is a way to show it. That is for number 12. Okay? Now, guys, if that didn't convince you, there's a lot of other methods. I'm just going to show you the answer key because why not? See, what I applied is basically this here. See, it's method 1. There's a lot of methods you can do. I think there's like 3 or 4. See? So, guys, just so you know, there's other ways to do it. For me, the most intuitive one is this one here, thinking about the areas. What is half of 82? Yada yada. See? ¿Cierto? Cool. I hope it helped. I hope more than anything you keep in mind the tools that you have. At the end of the day, that's the most important thing, guys. Don't think so much about, ooh, like, what's the trick in this exercise? What is this? What is that? Blah, blah. No, dude. think about the tools that the exercise gives you, okay? This is an exercise that is very good for understanding normal CDF. The day of tomorrow, you're going to have to look at an exercise that helps you understand better inventory normal or normal PDF. That is why my videos, in their name, in their title at the end, in parentheses, I put like buzzwords. Cierto? I put inventory normal, como yo, if you want to look at inventory normal, look at this, okay? If you want to look at the normal to the curve, look at that, you know, shit like that, see? So, think about the tools, think about that more than anything, and I hope it helped. That is number 12. All right, and for this 13 and last one, we have the very weird number 13. A boat travels 8 kilometers on a bearing, what the hell, of 315 degrees. And then a further 6 kilometers, again on a bearing of 45 degrees. Find the bearing on which the boat should travel to return directly to the starting point. All right, so this one, guys, is not that hard, but if you don't know what a bearing is, like you could not be more lost. Okay, so again, for a lot of these exercises in the IB, knowing these key buzzwords is important. All right, so what the heck is a bearing? When we talk about a bearing, it has to do with sort of like compass directions. Okay, I'm not so sure where the original term comes from, but just follow this idea. Okay, so you know how you have north, south, east, and west. When we talk about a bearing, it's a good way to give directions or indications of, you know, like which way you're going, stuff like that. And so let's say that the boat starts, okay, at 0, 0. See? If it travels 8 kilometers on a bearing of 315 degrees, we need to count these 315 degrees, okay? And it's a very special way in which you count them, all right? So have this intuition. North is going to be 0 degrees. East is going to be 90. South is going to be 180. West is going to be 270. And if you go all the way back, you get 360. See? Which is the same as 0 degrees. Now, some of you might be thinking, dude, what the hell are you saying? Okay? When you have a circle, okay, the degrees inside of a circle are 360. Okay? You have 360 degrees inside of a circle. On a line, you have 180. Okay? On a right triangle, you have 90 right there. See? Ah, okay. So on a circle, ¿cierto? Remember how I said that it's 360 degrees? Well, that's because if you cut the circle into 4 pieces, you have 90 degrees here, 90 here, 90 here, 90 here. Ah, so 90 times 4 gives you that 360. Okay? And that's why up here I said that east is 90 because it's these 90 here. That's why south is 180 because you're going to be doing 90 plus 90 gives you the 180. And for this last part, for the 270 of west, you are adding 90 again. See? And well, technically, if you add 90 again, you end up with 360. Okay? So that's just a little bit of context of degrees, bearings, where does it show up, stuff like that. So, intuitively, let's imagine we're starting at 0, 0. See? So we're starting right there. And they tell us, okay, we're traveling 8 kilometers on a bearing of 315. And so the 315 helps you, this helps you find the direction, okay, which direction you're going. And the 8 kilometers, of course, is going to be the distance. So 315 degrees means I am adding 90 here, 180 there, 270, and here, well, I don't add 360 because I would be going overboard, but I do add from 270 to 315, it's 45 degrees. So that means if I go like this, that means right here, right there, in the triangle that I'm now putting in dark blue, this has a degree of 45. How did I find that? Because I did 315 minus 270. Okay? Okay. And what's the distance of this? Well, what it's telling me, and I'm going to put the distance the boat travels in, I don't know, in brown, okay? So it travels 8 kilometers like this. Yeah. And then from here, it travels 6 kilometers on a bearing of 45. Now remember, a bearing of 45 means that if this is 90 and this is 0, that means 45 goes like this. Right down the middle, actually. See? So that means I have a bearing of 45 over here, traveling like this. Kapow. So I'm just going to put 6 kilometers there. See? And that means that I have an angle there of 45 right here. So this angle is 45. This angle in blue is 45. See? And then we need to find the bearing on which the boat should travel to return directly to the starting point. So then we have to see from here, okay, what is the angle it has to take to go all the way back. All right, that is the current context. Those are the angles that we know. See? So if I get a little more specific on what's going on, if I redraw this to make it a little more friendly, okay? All right, guys, and so now that we understood intuitively like what the exercise is actually telling us, we can now put it on a diagram that looks a little more pretty than the one we have up here. So what ends up happening exactly? Let's say that our guy starts at point A, okay? That means that on a bearing of 315, that means I have 270 degrees here, ¿cierto? Ta, 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 ta. And I go up 8 kilometers at a degree of 45. So that is how I end up with the 315. See? Kapow, kapow. That is the first part, okay? And just to leave this a little more pretty, I'm gonna put this dotted, all right? What happens then at a degree of 45, so that means from here, 45 degrees, right? I travel 6 kilometers, okay? So that's where the 45 degrees comes from. I'm gonna put a dotted line. We end up with that, okay? The dotted line is so that we remember why we end up with 45 degrees, okay? Then we end up with, I mean, they ask us then, like, okay, now you gotta come back. See, it says find the bearing on which the boat should travel to return directly to the starting point. So we gotta go back, right? And so this whole distance all the way back. Let me make that a straight line because some people get annoyed. Okay. And the bearing from here is, well, first we have these 90 degrees here, and then we have whatever is left, okay? Which is not so different, guys, than what I did down here. How did I end up with this 45? Well, because I said here we have 270, okay? And then we had to reach 315, I add 45, see? That is no different than what I did up here. I mean, I said, okay, I know that my bearing is, of course, this whole thing that I'm going to put in, I don't know, orange. See, so this is my bearing, okay? So the bearing I'm trying to find, I know is 90 degrees, right? This 90 there, plus what I'm going to call, whatever, I'm just going to call it theta, okay? And so basically, if I find theta in this context, I'm good to go, okay? So what else can I get from this? Now let's go piece by piece. See, something that is sort of cool or interesting about this is that there's a lot of straight lines going around. See, for example, because I'm drawing straight lines on these dotted lines, that means I have a straight line all the way down over here. Okay, and just to leave it pretty, I'm going to erase right there, which means I have 90 degrees there. And because this is 45 and this is 90, that means this is 45. Ah, okay, cool. Let's keep on adding to our diagram and see what we end up with, okay? So just to leave this pretty, that is a 45. That also means that up here, let me just leave it pretty. Da, da, da. That also means that up here I have 90 degrees. Okay. And these 6 kilometers goes here. And same conclusion as before with the other triangle. This is 45 degrees. Okay, now we're getting somewhere. See? That also means that if I do a dotted line over there, this is 90 degrees. I have my theta and some other angle that I don't have that might be necessary. Okay? Now, guys, I'm going to say this right away. See, there's a lot of different ways to solve this problem. What I'm going to show you is what I think is the most intuitive. There are other ways, and even the mark scheme has it different than what I'm about to show. Okay? I like to show what I consider to be the most intuitive approach. So, whatever, to each their own. Okay? Point is, because of these angles I just discovered, there's one key thing that I can conclude. Okay? So you know how I said that with the north-south, blah, blah, ¿cierto? North, south, east, west. I said that each of these is 90 degrees. Well, take a moment and focus on west to east. If you focused on west to east, what is that? That is a straight line. And so a straight line has 180 degrees. Okay. Remember how these dotted lines we said were straight lines? Okay. So that means that this here is 180 degrees. That means that the angle I'm missing is 180 minus 45 minus 45. That's going to give me this. Ah, okay. So that means I have 180 minus 90. That means I have 90. So this, putting it on a square, is 90 degrees. So now, ladies and gentlemen, we are dealing with a right triangle. My right triangle looks like this. I have 6 and 8 and 90 degrees. If I do some quick maths, this side is 10. Now, for you to believe me, we're going to apply Pythagoras theorem. See, so Pythagoras theorem looks like this. You use Pythagoras theorem when you have a right triangle. See, only when you have a right triangle, meaning you have 90 degrees here, you can use Pythagoras theorem. Now, hold up. Some of you might be thinking, okay, how do you know that you have to do this? And what I will answer is, all I know right now is that for me to get my bearing, which we said was 90 degrees plus this theta, I need to find theta. See? And theta is in this triangle on the top right. And so I need to get all the information about the triangle on the top right as possible. Okay? And so there's a chance that by finding this side here, I get more information about this whole triangle. Okay? And so basically, a lot of times in these trigonometry problems, I don't want to tell you like, first you do this, and then you do that, and then you get the answer, and blah, blah, blah. Okay? Let's be honest. A lot of the time, you're just trying to get new angles, you're trying to get new distances to see if you can come up with something. Okay? Which is also something good to keep in mind. When you're not sure what the fuck to do, okay, when you're not sure what the fuck to do, just get more information. Just get more information, see if you can come up with something, okay? So I know that I can get this side here, see, which is this side here. So we apply Pythagoras theorem. The key thing about Pythagoras theorem is that this guy is the long guy, okay? Your c squared is always going to be the hypotenuse, okay? So as long as you make sure that the c that you plug in is the long side, the hypotenuse, you're going to be fine. So in this case, the long side is obviously right here, so I'm going to have 6 squared plus 8 squared equals c squared. That means I have 36 plus 64 equals c squared. That means I have 100 equals c squared. That means c has to equal square root of 100. That means c equals 10. Okay, so I just discovered that this distance here is 10 kilometers. All right, cool. How does that even help me? Well, here you just need to get a little bit creative, okay? But the more exercises you see, the more intuition you're gonna get, all right? So because I need to find this theta angle, see, let's take a moment and look at where it is. You have theta right there, see? Where is theta? Theta is sort of in two places. it's in this triangle here. Okay, correct. But also, guys, it is in kapow. It's in this straight line. Ah, so what you're telling me is that I can do 45 degrees plus what I'm about to call x plus theta equals 180. Okay, so that means that once I get theta from there, I just plug it into my bearing and I'm good to go. So now my big challenge is how do I get x? Okay, so where is x? X is in this triangle. What do I know about this triangle? I know about this triangle that it looks like this. I have 6, 8, 10, 90 degrees. X is here. And from this position, a lot of you should know how to get it. Okay? From here, you just apply trigonometry. There's a couple of ways to do it. The most intuitive one, in my opinion, is this thing we call a sine rule. Sine rule, which is in your formula book, that looks like this. You have little a divided by sine big A equals little b divided by sine big B. So in sine rule, it works, I need you to remember, in pairs, okay? What kind of pairs? It works in pairs of angle with its side. Why do I say this? Because little a is going to be a side and big A is going to be an angle. Very visually, if you have angle A, that means you have side A. If you have angle B, that means you have side B. If you have angle C, that means you have side little c. Notice how the sides are little. Sides are little. Angles are big. See? So it actually matters the size of your letter in this case. Okay? So what pairs do I have here? Well, I have the pair of this 90 degrees with this 10. So that means I can already say 10 divided by sine 90. And I have this 8. I have this x, see, to side 8. So that means I have 8 divided by sine x. Okay, so what do I do from here? Well, what you can do is do this thing called cross multiply. Let me zoom in just to, make it a little more friendly, family friendly content. So you have 10 times sine x and sine 90 times 8. You just call it cross multiply, and we have fractions like this. Denominator with numerator, numerator with denominator, you end up with sine. Actually, yeah, you end up with 10 times sine x equals sine 90 times 8. If I want to get x alone, I'm going to end up doing sine x equals sine 90 times 8 divided by 10. And from this position here, you need to get x alone. See? Now, x in this context, remember the big letter, small letter, ¿cierto? So big letter, small letter, big is for angle. See? So right now, what's inside the sine, which is my x, is an angle. And so to get rid of this, to get x alone, better said, to get x alone, I need to do the opposite of what's next to it, see? And so here you actually do sine inverse. So sine inverse of sine x equals sine inverse of this whole thing. I know some of you are probably thinking, why the heck do you do sine inverse? And I'm about to show you, okay? So just chillax, I got you. So when you do sine inverse in this context, this goes away with this, and you end up with x equals this whole thing, okay? Why does it work like, why does it work that way? Imagine you have 2x equals 4, and I tell you, yo, you gotta solve this. How do you solve 2x equals 4? And a lot of you are just gonna say, duh, oops, I don't know what just happened. Okay, I'm back. A lot of you are just gonna say, duh, you divide by 2, see? Divide by 2 to both sides, compound, x equals 2, see? And I would say, yes, you're absolutely right, but let's talk a little bit about why. Why do you divide by 2 here? You divide by 2 here because this 2 is multiplying x. And what is the opposite of multiplication? Division. Okay. What is the opposite of sine? Sine inverse. Another way you can think about it is, what is the inverse operation to multiply? Dividing. What is the inverse operation to sine? Sine inverse. So when you do sine inverse, it's no different than like just doing the opposite of sine, okay? Fuck it. X is going to equal whatever this is, see? Make sure that you have it in, degrees for when you use sine inverse like this. You're going to have sine inverse is, pull up the fraction using alpha y equals, just to plug in more easily. You don't have to, but it's a little bit of a quality of life thing. Compound, so x equals 53 degrees. Yeah, let's just leave it as 53, whatever, okay? Yeah. So, x is 53 degrees. Cool. So that means that this angle up here that we put in green earlier is 53. That means that now I can find theta. Why can I find theta? Because let's remember, theta is part of a straight line. So the straight line is going to be the 3 angles that compose of it, which is theta, the 53, and the 45. So this x degree is now going to be 53 degrees. So for getting theta alone, I end up with theta equals 180 minus 45 minus 53. So theta is going to equal 180 minus 45 minus 53 gives you 82. And so now I plug that into my bearing. So we have that the bearing is the 90 degrees, which let's remember is the 90 degrees of here, ¿cierto? So those 90 degrees plus my theta, which is 82, is going to be my bearing. My bearing equals 172. And that, ladies and gentlemen, is how I suggest that you solve these type of problems. There are other ways. You can use this thing called arctan that shows up a lot. But for me, the most intuitive is sticking to the tools that you already have. See? The sine rule, okay? Making straight lines with the dotted lines, stuff like that. Regardless of that, use the method you feel most comfortable with. And I helped you understand a little bit more the difference between bearing and other stuff, okay? So remember, bearing intuitively is like your direction, and distance, they're gonna give you the distance, okay? But yeah, see. Also remember that north is 360 or 0, east is 90, south is 180, west is 270, which is no different than a circle, okay? All right, ladies and gentlemen, that is for number 13, and that is actually for this whole exam. I hope it helped. Take it easy. Good luck and everything.